Piebald rats and selection **** Piebald rats and selection, an experimental test of the effectiveness of selection and of the theory of gametic purity in Mendelian crosses by W. E. Castle and John C. Phillips, Washington, D.C. Published by the Carnegie Institution of Washington 1914 Carnegie Institution of Washington. Publication number 195, paper number 21 of the Station for Experimental Evolution at Cold Spring Harbor, New York, from the Laboratory of Genetics of the Bussey Institution. Copies of this book were first issued the 18th of February, 1914. Press of Gibson Brothers, Inc., Washington, D.C. Contents. Page. Introduction 5 Material and Methods 7 plus Selection Series 9 - Selection Series 12 Return Selection 13 Crosses with Wild Rats 16 Crosses with Black Irish Rats 18 plus Selection of Extracted Hooded Rats 20 Crosses of the Plus Race with the Minus Race 22 Summary of Results 22 Discussion 23 The Mutant Series 25 Bibliography 31 Tables 32 to 54 Explanation of Plates 56 Piebald Rats and Selection. Introduction. The fundamental importance of Mendel's law of heredity is generally recognized among biologists. It is a working hypothesis whose utility is fully substantiated by abundant results daily increasing in amount. But biologists are not in agreement as to how much this law includes. All perhaps would agree that it implies the existence in the germ cell of specific determiners essential for the production of particular characteristics in the offspring. Further, no one probably will object to the statement that it implies a dual or duplex condition of the zygote as regards determiners and a simple or simplex condition of the gamete. Thirdly, the fact will be admitted by all that most Mendelizing characters are wholly independent of each other in heredity, for which reason we are forced to suppose that their determiners are distinct within the germ cell. But beyond these few generalizations, great diversity of opinion exists. As regards the very nature and function of the determiners, some consider them unvarying, and explain the observed variation of Mendelizing characters in organisms as due to a modifying action of other determiners. At one time even a modifying action of other determiners was denied, and the theory was advanced that the gametes extracted from a Mendelian cross are pure as regards the single characters which may have been concerned in that cross. Investigations carried out by Castle have done something to dispel this idea. In particular, it was shown, Castle, 1905, 1906, Castle and Forbes, 1906, that in guinea pigs, polydactylism, long hair, and rough coat are Mendelizing characters which are affected in the degree of their development by crosses, that is, when these characters are extracted from crosses the characters are not exactly the same as before, hence the gametes are not pure. The experimental result is not denied, but in order to save the substance of the theory its advocates now suppose that the determiners have not changed, but in consequence of the cross certain modifiers have become associated with them which change their appearance in the organism. The real unchanging thing is now called the genotype, its appearance the phenotype. In this genotype theory we are dealing only with a new and more refined aspect of the theory of pure gametes. It is not a necessary part of Mendelism, not even an original part, but it is very important for us to know whether it is true or not. For if it is true, selection unattended by hybridization is largely a waste of time, as de Vries and Johansen have maintained, and Jennings and Pearl have reiterated. The investigation which we are about to describe was started 6 years ago to test the validity of the theory of pure gametes which was then current. Pure genes had not yet been invented. The investigation has been in continuous progress ever since, and while we expect to continue it further, it seems to us desirable that the results already obtained be presented for criticism. Some conception of the work entailed in the investigation may be gathered from the statement that we have during its progress reared and studied the color pattern of over 25,000 rats. A long and arduous investigation of this kind has been made possible by a series of grants from the Carnegie Institution of Washington made to the senior author, for which he here makes grateful acknowledgement. Thanks are also due to Dean W. C. Sabine, of Harvard University, for encouraging and supporting the work in a variety of ways. Material and methods. In June 1906, Dr. Hansford McCurdy completed, under the direction of the senior author, a study of the inheritance of color in rats. His studies had shown that the piebald pattern of hooded rats behaves as a Mendelian recessive character in relation to the uniform or nearly uniform coloration of wild rats, but that the hooded pattern, when extracted from a cross with wild stock, shows a different variability, the pigmentation of the extracted recessives being increased in extent. This result was interpreted as showing the unsoundness of the current doctrine of purity of the gametes in Mendelian crosses. Upon the conclusion of Dr. McCurdy's experiments, the pedigreed stock which he had used was not entirely discarded. A certain portion of it was utilized for new experiments designed to show whether the hooded coat pattern can be modified by selection unattended by crossbreeding. 2 series of selections were started in October 1907, in one of which animals were chosen as parents which had pigmentation as extensive as possible. This we may call the plus series. In the other series, animals were chosen as parents which had pigmentation as restricted as possible. This we may call the minus series. During the academic year 1906-07, the experiments were in immediate charge of Mr. W. G. Venel. During 1907-08 the plus series was in charge of Mr. H. S. Rand, while the minus series was in charge of Mr. F. C. Bradford. Throughout this time the experiments were closely supervised by the senior author, who assisted in the grading of every litter of young. In October 1908 the junior author began his association in the experiments, which has continued up to the present time. Throughout these 5 years he has looked after the details of the experiments almost continuously, but both authors have in most cases taken part together in the grading of the young, and in no case has the grading been done except under the immediate supervision of one or the other of the authors. This fact is stated to show that the personal element in the grading has been kept as constant as possible. In the tabulation of results and computation of statistical constants, the authors have worked together. This statement of results is written by the senior author. During the year 1906–7 the young rats were graded by the method used by McCurdy and Castle, 1907, that is, the back stripe was measured and a calculation made of the percentage of the dorsal surface posterior to the hood which was pigment. But on account of the irregular outline of the back stripe in many individuals, the method of measurement was found to be at best a rough one, as well as extremely laborious. Accordingly, in the summer of 1907 a set of arbitrary grades was adopted, which is shown at the top of Plate 1. Each young rat was classed in that grade which it most nearly approached in amount of pigmentation. Skins of rats graded from -3¼ to +4¾ are shown in the middle and lower rows of Plate 1. The grading was done when the rats were about 3 or 4 weeks old, at which time selected individuals were reserved as the parents for a later generation, the remainder being discarded. This method has been followed ever since its adoption, and the data thus obtained are summarized in the tables, which cover the breeding operations of a little more than 6 years, 1907 to 1913. The grouping of the young in a series of generations is only approximately accurate, for practical considerations have often led us to mate together animals which belonged to different generations of offspring. When, for example, an animal of generation 2 was mated with one of generation 4, the question would arise, to what generation do the offspring belong? In deciding this question we simply added 1 to the mean of the generations to which the respective parents belonged. In the foregoing case this would be 2 plus 4, /2 plus 1 equals 4. In case one parent belonged to generation 2 and the other to generation 3, a fractional result would be obtained, thus, 2 plus 3, /2 plus 1 equals 3½. In making up the summaries of the generations as given in the tables, offspring like the foregoing, of generation 3½, were divided equally between generations 3 and 4. Alternate litters of young as recorded in the ledger being assigned to each. Offspring belonging to generations 2 3/4 and 3¼ were tabulated in generation 3, those belonging to generations 3 3/4 and 4¼ were tabulated in generation 4, etc. While, therefore, the generations as tabulated overlap, it is clear that they include groups of offspring of selected parents, each the result of one additional selection over the preceding group. The early generations include too few individuals to be of much statistical value, but where the number of offspring rises to 500 or over, the statistical constants acquire undoubted value. The data have been given in the form of correlation tables which will repay careful study. In the tables a single entry has been made for each individual offspring in that row which corresponds with the mean grade of its 2 parents. Thus, if one parent were of grade 2 and the other of grade 2½, the offspring would be entered in the row 2¼ along with the offspring of parents both of grade 2¼ offspring of parents whose mean grade fell between the rows given in the tables were divided equally between the adjacent rows, alternate litters being assigned to each. Thus, if the mean grade of the parents were 2, alternate litters of offspring would be entered in row 2 and in row 2 1/8. Plus selection series. This series begins with pairs ranging in average grade from plus 1.87 to plus 3. From these parents were obtained 150 young, which range in grade from plus 1 to plus 3, as is shown in Table 1. It will be observed that the lower grade parents have on the average lower grade offspring than the higher grade parents. But in no case is the average grade of the offspring as great as that of their parents. Thus 1.87 parents had 1.82 offspring, average grade. 2.00 parents had 1.76 offspring, 2.25 parents had 1.87 offspring, and so on to 3.00 parents, which had 2.35 offspring. There is a falling back in grade or regression of the offspring as compared with their parents, which increases in amount as the grade of the parents becomes higher. See column regression in Table 1. The parents of this first generation were chosen because of their high grade. They were all probably in grade above the general average of the population from which they were selected. In the case of those which deviate most from the general average, the regression is greatest, as we should expect. This phenomenon of regression, which is a very general one in cases of selection, was first observed by Galton in selecting sweet peas of varying size from a mixed population. Later Johansen, who repeated the experiment with beans, found that by pedigree culture he was able to break the mixed population up into pure lines within which, considered singly, no regression occurred. We shall need later to return to this subject and consider whether pure lines free from regression exist or can be produced as regards the hooded pattern of rats. Returning to the examination of Table 1, since the high-grade parents produce higher-grade offspring than do the low-grade parents, it is evident that we might hope by further selection either to isolate a pure line of high-grade rats which would be free from regression and therefore stable, or else to advance the grade of the offspring still higher, even though regression persists. As a measure of the extent to which high-grade parents have high-grade offspring and vice versa, in each generation, we may employ the well-known correlation coefficient. This for Table 1 is 0.30. The second generation in the plus series, Table 2, includes the offspring of parents which appear as offspring of the higher grades in Table 1, together with a few individuals which appear in Table 2 both as offspring and as parents of other offspring, by reason of their having been mated with Generation 1 individuals and so having produced Generation 1½ offspring, as explained on page 8. To obtain larger numbers of offspring, several new pairs were added to the experiment in this generation, which do not appear in Table 1 either as offspring or as parents, but which were derived from the same general stock as the parents of Generation 1. Their inclusion here accounts for the very low range of the offspring in Table 2, which extends from -1.00 to +3.75. The parents' range, means of pairs, extends from 2.00 to 3.12. The grand average of the parents is 2.52, that of the offspring is 1.92. The correlation between grade of parents and grade of offspring is 0.32. From this point on in the series no new stock was added and each generation of offspring furnished the parents for the following generation, except for the slight overlapping of generations when parents of different generations were mated with each other, as has already been explained. In Generation 3, Table 3, the parents ranged from 2.12 to 3.37 in grade, the offspring from 0.75 to 4.00. The mean of the parents was 2.73, that of the offspring 2.51. The degree of correlation between parents and offspring is expressed by the coefficient 0.33. A perfect correlation would give 1.00. In Generation 4, Table 4, the selection of parents became considerably more rigid. Most of the parental pairs were of grade 3 or higher, their average being 3.09. The average grade of the offspring was 2.73, their range extending from 0.75 to 3.75. The correlation in this generation fell very low, to 0.07. Not because of a lessened regression but rather because of a very high regression on the part of the offspring of high-grade parents. In Generation 5, Table 5, the grade of the selected parents ranged from 2.75 to 4.12, its mean being 3.33. The offspring, showing the usual regression, ranged from 0.75 to 4.25, their mean grade being 2.90. The correlation between parents and offspring in this generation was 0.16. The number of individuals comprising this generation of offspring was 610. It is scarcely necessary to discuss separately the correlation table for each of the next 8 generations, tables 6 to 13. The number of offspring rises to a maximum, 1,408, in Generation 8, Table 8, then declines to less than 200 in Generation 13. But as this generation and the preceding one are still being produced, it is probable that the number recorded will be considerably increased before the generation is complete. The means of parents and offspring and the other statistical constants for the several generations can be most easily compared by reference to Table 14. Leaving out of consideration the exceptional generation, 2, the following will be observed. 1. The mean of the selected parents has steadily advanced throughout the series, as has also that of their offspring. 2. The variability, standard deviation, of the parents as a group has decreased somewhat as increase in numbers made a more rigid selection possible, that of the offspring has undergone a similar change. 3. The correlation between parents and offspring has not materially changed. The average of the correlation coefficients for the entire series is 0.194. For the last 3 generations it is 0.175. For the 3 preceding generations it is 0.141. For the 3 which precede those it is 0.185. While for the first 4 generations it is 0.253. In every case the correlation is positive, that is, the higher grade parents have higher grade offspring and vice versa. 4. The offspring as a group average lower in grade than their parents, that is, their mean regresses on that of the selected parents, but because of the higher mode about which variation occurs in each generation, certain of the offspring are of higher grade than their parents. Thus an elevation of the grade of the parents in the next generation is made possible. 5. With the selection of more extreme parents, the absolute regression of the offspring has not increased, but on the contrary has slightly diminished, that is, the advance made by the parents is retained by their offspring. In Table 15 have been brought together for comparison the means of the several horizontal rows of Tables 1 to 13. By examining the vertical columns of Table 15, the mean grade of the offspring of parents of a particular grade in any generation may be compared at a glance with that of parents of the same grade in any other generation. By running the eye down the columns, it will be observed that the mean grade of the offspring tends to increase upon repeated selection. Thus parents of grade 3.75 appear first in generation 4, the grade of their offspring being 2.75. The offspring of such parents in subsequent generations grade in order 3.07, 3.22, 3.35, 3.49, 3.50, 3.69, 3.75, and 3.83, 12th generation not complete. The difference between parents and offspring in this series grows less and finally disappears altogether. If the grade of 3.75 parents in this series is compared with the grade of all offspring in the corresponding generations, we have the following table: a generation. Mean of offspring of 3.75 parents. Mean of offspring of all parents. For 2.75, 2.735, 3.07, 2.906, 3.22, 3.117, 3.35, 3.208, 3.49, 3.489, 3.50, 3.54, 10, 3.69, 3.73, 11, 3.75, 3.77, 12, 3.83, 35 individuals, 3.94, 590 individuals. In generation 4, the 3.75 parents represented the most advanced individuals of the series, a whole grade in advance of the general average of the race. Their offspring showed a correspondingly large regression. The general average of the race steadily advanced in later generations until in generation 11 it equaled that of the 3.75 parents, then the regression vanished. In the following generation, 12, which is still incomplete, but in which the average of the offspring thus far is 3.94, the 3.75 group of parents, which are now below the average of the race, actually produce offspring of higher grade than themselves, viz. 3.83. It will thus be seen that the regression is uniformly toward the mean of the race and changes its direction when that mean changes its position with reference to a particular grade of parents. This conclusion is supported by other columns of Table 15, but is best illustrated by this particular case because here the selection has extended over a greater number of generations than elsewhere in the series. If one examines the horizontal rows of Table 15, he finds in general that numbers increase toward the right. Exceptions are commonest toward the ends of the rows where fewest individuals are represented. This increase means that, within any generation, as the grade of the parents rises, that of their offspring rises also. Since in general the selected parents are above the general average of the race for the time being, regression is naturally downward in nearly all cases. From what precedes we may conclude, 1. That in this series of rats the somatic character, appearance, of an individual is in general a true indication of its germinal character, since the higher the grade of the parents the higher the grade of the offspring, and vice versa, but that, 2. The somatic character of an individual is not a perfect index of its germinal character, since the offspring of aberrant individuals are less aberrant than themselves, i.e., the offspring regress toward the mean of the race, yet that, 3. By selection of plus variations we can displace, in a plus direction, not only the mean of the race, but also the upper and lower limits of its variation, the total amount of variability, standard deviation, being thereby only slightly decreased. Minus selection series. This series begins with selected parents ranging in grade from -1.25 to -1.87. Their average, if each pair is weighted in proportion to the number of its offspring, is -1.46. The offspring, Table 16, like the offspring of the original plus selections, regress toward grade 0. They range in grade from plus 0.25 to -2.00. Their mean being -1.00. The total number of offspring recorded in this generation is only 55, this being too small to warrant the calculation of a correlation coefficient. Generation 2, Table 17, is somewhat larger, but still too small to make statistical constants based upon it of much consequence. The offspring show substantially the same range of variation as in the previous generation, but with a slightly higher average, -1.07. The coefficient of correlation, -0.03, is negative, but too small to be significant. The record of the next 11 generations will be found summarized in Tables 18 to 28, or in more condensed form in Tables 29 and 30. Generation 13, Table 28, is still incomplete. The mean of the parents steadily rises from -1.56 in generation 3 to -2.50 in generation 13. the mean of the offspring rises by like increments from -1.18 in generation 3 to -2.39 in generation 13. There is throughout these generations a positive correlation between parents and offspring. This amounts on the average to 0.137 as compared with 0.193 observed in the plus selection series. The absolute change in amount of pigmentation is no doubt less in the minus selection than in the plus selection series. But if the change were recorded as percentage decrease of pigmentation in one case and percentage increase in the other, the change indicated would probably be as great in one as in the other. In the minus as in the plus series we observe, 1. The character of the offspring varies with that of the parents. High-grade parents have high-grade offspring and vice versa. 2. The variability of the race, as indicated by the standard deviation, undergoes some reduction and the limits of variation, both upper and lower, are displaced in the direction of the selection. 3. The regression from a new and extreme class of parents is at first large, but decreases as the selection is repeated and finally disappears altogether when the average of the race becomes equal to the particular grade under discussion. Return selection. The plus and minus selection series already described make it clear that one can, in a race of hooded rats, either increase or decrease the average pigmentation at will, and at the same time secure more advanced stages either of pigmentation or of depigmentation than those previously occurring in the race. The question now arises, are these changes permanent? Will these displaced means retain their new position, if the race is left to itself, or will the newly obtained stages vanish as soon as selection is suspended? A presumption that the changes will prove permanent is afforded by the gradual decrease of regression and its final reversal in the case of offspring of a particular grade, upon repeated selection made in the same direction. See page 12. But in order to test the matter more directly and thoroughly, the experiment has been repeatedly made of reversing the course of selection, after it had been in progress for several generations, with a view of ascertaining whether the return toward the former condition of the race would be made more speedily and easily than the original departure from it had been. The first experiment of this sort was a return selection from generation 6. And 6.5, of the minus selection series. The parents of generation 6, table 21, averaged -1.86 in grade. The average grade of their offspring was -1.56, a regression of 0.30. The range of the offspring extended from 0 to -2.50. Some low-grade offspring were chosen for a return selection series, table 31. The mean grade of the selected pairs ranged from -0.37 to -0.87, their mean being -0.60. These parents produced 118 offspring, whose average grade was -1.28, a regression of 0.68 in a direction contrary to that of the regression in the minus selection series. The large amount of the regression might seem to imply that it was even more difficult to return toward the former state of the race, in the neighborhood of 0, than it had been to depart from it, but this cannot be insisted on, because the number of individuals under observation is not sufficiently large. To test the reality and permanency of the reversed regression, the selection was repeated 5 additional times, altogether 6 successive return selections being made with the idea of undoing what had been effected by 6 original selections in an opposite direction. The result of the second successive return selection is shown in Table 32. The parents here were of grade -0.50 and they produced 19 offspring of the average grade -0.95, a regression of 0.45 away from 0 as before. Table 33 shows the result of the third return selection. Individuals entered in Table 32 as offspring appear here as parents. Only those pairs which were of mean grade, -0.25 or -0.37, should really be regarded as a third return selection. They gave offspring with mean grades of -0.63 and -0.86 respectively, which show regression of 0.38 and 0.49 away from 0. But Table 33 shows also the character of young produced by -1.12 and -1.25 parents in this same third return selection generation, i.e., by unselected parents of the generation in question. Their young also regress away from 0, that is, in the direction of the original selection. The -1.12 parents produced -1.61 offspring, a regression of 0.49, while the -1.25 parents produced -1.35 offspring, a regression of 0.10. For Table 33 as a whole, the regression away from 0 averages 0.31. A fourth generation in the return selection series is summarized in Table 34. The parents are of mean grade -0.63, their 50 offspring are of mean grade -1.17. A regression amounting to 0.54 away from 0 and in the direction of the 6 generations of original selection. Table 35 contains the results of the 5th generation of the series. The parents are here of mean grade -0.65. The number of offspring is very small, 13. But they nevertheless show the reversed regression which characterized the 4 preceding generations. Their mean was -0.75, a regression of 0.10 away from 0. A 6th and final generation in this return selection experiment is summarized in Table 36. It includes 36 offspring of mean grade -0.39, the mean of the parents being -0.26, a regression of 0.13 away from 0. It will be seen, therefore, that the effect of the 6 original selections had not been entirely overcome by an equal number of return selections. The reason for this is obvious. Much smaller numbers are concerned in the return selections than in the original minus selections. The return selections are accordingly less efficient. Nevertheless, after the 6th return selection we find that 1 in 6 of the offspring have plus grades and their average is lower, that is, less minus, than the offspring in the minus series after a single generation of selection. Compare tables 16 and 36. The amount and persistency of the reversed regression in this series show clearly that return selection is not easier or more rapid than the original modification of the race by selection, but that selection in either a plus or minus direction has cumulative and permanent effects. Further support for this conclusion is furnished by return selections, one each, made from the 7th generation, from the 8th generation, and from the 11th generation of the minus selection series. See tables 37, 38, and 39. Generation 7, table 22, was produced by parents of average grade -2.01. Their offspring were of average grade -1.73, a regression toward 0, amounting to 0.28. Certain pairs of these offspring of grade -0.75 and -0.87, mean -0.78, constitute the return selection from generation 7. Table 37. They had 33 offspring of average grade -1.15, a regression away from 0 amounting to 0.37. Generation 8 of the minus selection series, table 23, was produced by parents of mean grade -2.05. Their offspring were of mean grade -1.80, a regression toward 0 of 0.25. Certain pairs of these offspring of grades -0.50, -0.62, and -1.00, mean -0.72, when chosen as parents, produced 41 young of mean grade -1.51, a regression away from 0 amounting to 0.79. See table 38. Generation 11 of the minus series, table 26, was produced by parents of mean grade -2.30. The offspring were of mean grade -2.15, a regression of 0.15 toward 0. A pair of the offspring of mean grade -1.62, table 39, produced 16 young of mean grade -1.95, a regression of 0.32 away from 0. This result shows that the selected race had now passed the point represented by the grade of the parents, -1.62, and the offspring regressed toward a racial mean as advanced as the most extreme individuals obtained previous to selection. To show that, in the plus selection series, a return selection has a result similar to that just described, two experiments may be cited. The 6th generation of the plus selection series was produced by parents of mean grade 3.52, and their offspring were of mean grade 3.11, a regression toward 0 amounting to 0.41. Certain of these offspring of mean grade 2.00, when chosen as parents, produced 17 young of mean grade 2.36, a regression away from 0 amounting to 0.36. See table 40. The 11th generation of the plus selection series, table 11, was produced by parents of mean grade -3.97. Their offspring were of mean grade -3.78, a regression of 0.19 toward 0. Certain of these offspring, ranging in grade from -2.62 to -3.25, Table 41, mean -2.79, produced 53 young of mean grade -3.32, a regression away from 0 amounting to 0.53. The regression in this case, as in all those previously described, was toward the racial mean of the previous generation, which, however, it has in no case reached. This can have but one meaning. The genetic character of the hooded rat is in a general way correctly indicated by its somatic character. Selection is therefore immediately effective, whether plus or minus in character, and whether or not preceded by selection in the same direction or in an opposite direction. But regression may be expected from the character of aberrant parents back toward the normal of the previous generation, yet this regression will in general be less than the departure of the aberrant parents from the normal of their generation. If one desires in such a case to obtain continuous and progressive departure from the normal in either a plus or a minus direction, he need only select continuously in the desired direction. Crosses with wild rats. As a further test of the permanency of the modification effected by selection in the hooded pattern of rats, crosses have from time to time been made of the selected races with a pure wild stock, i.e., with ordinary wild animals caught in traps. In all cases the wild animals used were known to be homozygous as regards grey coat and self-pattern, since when crossed with black hooded animals they produced only grey self-offspring. In such crosses the hooded pattern is recessive, the F-offspring being indistinguishable from ordinary wild grey rats except for the possession of a white patch of varying size upon the belly, but even this may be lacking. See Plate 2, male sign 8000, 8018, and 8021. The grade of the hooded young extracted from a cross with wild animals corresponds in a general way with the grade of the hooded animal used in making the cross, as the following cases will show. Compare also plates 2 and 3. A female of grade -1.87, belonging to generation 2.5, minus series. Compare tables 2 and 3, was crossed with a wild male. See Plate 2, female sign 6176. Among her F descendants, compare Plate 2, 8070 to 8078, occurred 62 hooded individuals, whose grade distribution is shown in Table 42, first row. Their mean grade is plus 0.31, although the uncrossed race of the same grade and generation gave offspring of mean grade about -1.20. The cross, therefore, had apparently increased the pigmentation of the extracted hooded recessives. This idea is supported by the result of a control mating of the particular female used in making the cross. When she was mated with a hooded male of the same grade as herself, she produced 3 young, all of grade -1.00. The extracted recessive grandchildren, as a group, show greatly increased pigmentation as compared with this, but vary greatly in the extent of the increase. Some show very little modification, others very much, the most extreme individual being of grade plus 3.50. It was undoubtedly out of just such modified recessive individuals as this that the material for our initial plus selections arose. To this point we shall return later. The F, or second generation, offspring, however, include about one hooded individual in 4. In a total of 962 F young, 230 were hooded, or 24%. This summary includes only those litters in which dominants as well as recessives were recorded. In many litters only the hooded young were recorded, as the special object of the investigation was to ascertain whether the extracted recessives were like the pure hooded race in grade or not. In the above summary also the hooded grandparent was in every case a female. The reciprocal cross is more difficult to obtain, but one wild female rat, caught in 1911, has bred quite regularly in captivity, though each time she has murdered her hooded mate prior to the birth of the young. Her F grandchildren derived from matings with males of the minus series include 32 hooded and 96 non-hooded individuals, exactly 25% hooded. A second cross of selected animals of the minus series was made between a wild male and 4 females of grade -2 derived respectively from generations 5 1/4, 5 1/2, 6 1/2, and 7. As a group these mothers are more nearly comparable with generation 6, table 21, than with any other uncrossed group. As the F progeny of these 4 mothers by a wild male were mated inter se, it is possible to deal with their hooded grandchildren only as a group. The character of these is indicated in the second row of table 42. They number 48 individuals and have a mean grade of plus 0.25. Showing a modification in a plus direction similar to that observed in the previous case. A third cross in which the minus series is concerned was made between females of grade -2 and -2.25, generation 10, and wild males. The F offspring include 91 hooded individuals classified as to grade in the third row of table 42. Their mean grade is plus 0.24, confirming fully the results obtained in the 2 previous experiments. With these 3 cases we may compare 3 cases in which animals of the plus selection series were crossed with a wild male. See the last 3 rows of table 42. Females of grade plus 3.00, generation 3, were crossed with a wild male. From this mating resulted 21 hooded grandchildren, ranging in grade from plus 1.75 to plus 3.50, mean plus 2.56. These grandchildren, it will be observed, in no case are of minus grade, as are about half the grandchildren when the grandparent is of minus grade. There is also no clear evidence of modification of the hooded character by the cross in this case. The grade of the extracted hooded individual is just about what uncrossed individuals of grade plus 3.00 produced in the corresponding generation of the plus series. In the next case, two females of the plus series, belonging to generations 5 and 6, respectively, were crossed with a wild male and their children were bred in Teresi. There resulted 38 hooded grandchildren, as shown in the next to the last row of table 42. The range of the grades of these hooded grandchildren was similar to that of the grandchildren in the foregoing case, but their mean was somewhat higher, as we should expect, since they are descended from more highly selected individuals, for the hooded grandparents in this case were of grade plus 3.25, generation 5, and plus 3.50, generation 6, whereas the grandparent in the foregoing case was of grade plus 3.00, generation 3. It is a noteworthy fact that in both these cases the wild cross does not seem to have increased the pigmentation in extracted hooded individuals, as it did when the minus series was crossed, but rather to have diminished it, yet the difference between observed and expected is not great. We might disregard it altogether, if a similar but more striking result were not observable in the third case as well as in another series of crosses presently to be described. The third case, last row of table 42, involves a cross between a female of grade plus 4.25, generation 10, plus series, and a wild male. The F offspring includes 16 hooded individuals of mean grade plus 3.15. Animals of this grade in the uncrossed race in this generation produced young of mean grade plus 3.84. Before leaving this subject, it is important to observe the considerable difference between the extracted hooded grandchildren of the minus series rats, as a group, and those of the plus series. The latter is unmistakably a plus series group, the former is on the borderline between the two series. Compare plates 2 and 3. Crosses with black Irish rats. As a control on the results given by the wild crosses, we may examine the results obtained by crossing the plus and minus selected races with a black Irish race. The Irish race used for this purpose consisted of animals black everywhere except on the belly. On the system of grading used in this paper, they would range from plus 4½ to plus 5¾ plus 6 being an all-black rat. Crosses of minus series hooded rats with Irish produced Irish F offspring with rather more white on the belly than the Irish parents possessed. In the F generation, hooded individuals reappeared in approximately the expected 25%. In a total of 764 second generation young, 171, or 22.4%, were hooded. The grade of pigmentation of these extracted recessives as compared with that of their hooded grandparents we may now consider, as was done in the case of the wild crosses. See Table 43. 6 individuals of the minus selection series, of generation 3½, and of mean grade minus 1.50, were crossed with Irish rats producing Irish offspring which were mated in Teresi. Among the grandchildren appeared the usual proportion of recessives, hooded, 90 in number. The distribution of these as regards grade of pigmentation is shown in the first row of Table 43. Their mean grade is minus 0.62, that of uncrossed hooded rats of the same grade as the hooded grandparents being -1.31 in generations 3 and 4. In other words, the cross has considerably increased the pigmentation in the hooded grandchildren over what was to be expected had the cross not taken place. Nevertheless, the increase in this case is less than in the similar cross with wild rats. Compare Table 42. In the second row of Table 43 is shown the grade distribution of extracted hooded grandchildren of two mothers of grade -1.87 and generation 4. The mean of the 53 hooded grandchildren is in this case -0.73, that of uncrossed hooded parents of the same grade and generation being 1.18. This average is probably too low. An examination of the means of adjacent classes, Table 19, indicates that it should be about 1.35. In the third row of Table 43 is shown the grade distribution of the extracted recessive grandchildren of a -2.00 male, series rat, of generation 7.5. The 66 grandchildren are of mean grade -0.94, expected -1.75. Comparing the three experiments, first three rows of Table 43, we see that the more advanced grandparents, in grade and generations of selection, have the more advanced grandchildren, but in every case these are less advanced than grandparents of the same sort would have given had they not been crossed. Hence crossing with Irish has clearly had the effect of increasing the pigmentation in the minus series in the same way, but in lesser degree, as did crossing with wild animals. The results of crossing hooded rats of the plus series with Irish ones are shown in the last two rows of Table 43. Several rats of mean grade plus 2.25 and of generation 2 were crossed with Irish, and their Irish young were then bred inter se, producing 239 hooded grandchildren. These ranged in grade from -1.00 to plus 3.25, their mean being plus 1.27. The grade of uncrossed rats of like grade and generation to the hooded grandparents is plus 1.80. Hence here, as in the cross with wild rats, the pigmentation has not been increased, but decreased by the cross, contrary to what we should expect. Further, the departure from expectation is greater in this cross than in the wild cross. These conclusions are supported by the results shown in the last row of Table 43. In the experiment here recorded, a plus 3.00 rat of generation 3 was mated with an Irish rat. The hooded grandchildren derived from this cross were, as shown in the table, of mean grade plus 0.95. Expected about plus 2.50. Since the number of animals recorded in this experiment is comparatively small, the quantitative result is less important than that of the foregoing experiment, but qualitatively the two are in entire agreement. The various crosses of the selected minus and plus series with wild rats and with Irish rats respectively are consistent with each other. In every case the cross increases the pigmentation of the minus series and decreases that of the plus series, in other words, it undoes the work of selection to some extent. Does this mean that the condition created by selection was in reality an unstable one, so that an outcross tends to do away with it? We do not think so, but to this question we shall return again. The question might be asked whether the modifications produced in the selected races by a cross with wild or Irish stock are likely to be more or less permanent than those produced in unselected races by the same means. A single experiment was made which bears on this question in relation to the Irish cross. One of the -2.00 grandchildren recorded in the third row of Table 43 was mated with -2.00 individuals of the uncrossed stock of the minus series and produced 9 young of mean grade -0.63. The expectation for the uncrossed race of the same grade and generation being about -1.90. In other words, this extracted -2.00 individual regressed, in breeding, as if it really had been affected by the cross, even though it did not show it. But the number of young is so small that no emphasis should be placed upon this result. From the experiment recorded in the last row of Table 43 were obtained extracted individuals of mean grade +1.37, which as parents produced 16 young of mean grade +1.68, or, in other words, offspring about like themselves. Hence the changes effected by a cross are permanent, like those effected by selection. Plus selection of extracted hooded rats. It has been suggested that the original material out of which the plus series came consisted of modified individuals produced by a cross with the wild race. This was not known positively to be so, because part of the original stock, with which MacCurdy worked, consisted of hooded black and hooded grey rats captured in company with grey self and black Irish rats and albinos. Subsequent experiments showed that ordinary albino rats, if crossed with wild grey ones, will produce in all these classes of individuals. This indicated pretty clearly that the particular colony which had fallen into our hands had probably arisen by the crossing of an escaped albino rat with wild ones. But it still remained uncertain what sort of hooded pattern the escaped albino had transmitted and whether or not this had been influenced by the wild cross. We therefore determined to ascertain whether out of our minus series crossed with wild a plus series could be derived. To this end certain of the extracted hooded individuals, entered as grandchildren in Table 42, Row 1, and descended from a single hooded individual of grade -1.87, generation 2.5, were mated inter se, thus producing an F generation, Table 44, second row. The selected individuals were the aberrant male of grade +3.50 and females of grade +1.50, so that the mean grade of the chosen parents, extracted from the crossed minus series, was +2.50. They had 34 young ranging in grade from 0 to +3.50. Mean +2.06, a regression of 0.44 toward 0, repeating the phenomenon regularly found in both selection series. In this same experiment some F parents of mean grade -0.75 had 19 young, first row of Table 44, whose mean grade was -0.04, a regression of 0.71 toward 0. We should expect the regression of the offspring of such parents to be less than that of the offspring of the -2.50 parents, and so it would be if it were not for one aberrant individual. Larger numbers of offspring would undoubtedly have given the expected result. From among the F offspring were chosen parents for the next generation, F. The chosen parents ranged in mean grade from +2.25 to +3.12, Table 45, average +2.52. They produced 205 young ranging in grade from -0.25 to +3.50, mean +1.86. A regression of 0.66. The parents for the next generation, Table 46, ranged in mean grade from +2.00 to +3.00, the mean being +2.27. They produced 119 offspring of mean grade +2.06. A regression of only 0.21. Table B. Comparison of the present series with the more general plus selection series. Selection. Present series. General, plus, series. Mean, parents. Mean, offspring. Regression. No of offspring. Mean, parents. Mean, offspring. Regression. No of offspring. 1 2.50 2.06 0.44 34 2.51 2.05 0.46 152 2.52 1.86.66 205 2.52 1.92.60 471 3 2.27 2.06.21 119 2.73 2.51.22 341 4 2.69 2.41.28 194 3.09 2.73.36 444 5 2.77 2.32.45 97 3.33 2.90.43 610 6 3.08 2.67.41 45 3.52 3.11.41 861. The parents chosen from among these offspring ranged in mean grade from +2.37 to +3.25, average +2.69. They produced 194 offspring of grade +0.50 or higher. F. Table 47, the range for the first time lying wholly in the plus direction. The mean grade of the offspring was +2.41, a regression of 0.28. The parents of the next generation, F. Table 48, range in mean grade from +2.62 to +3.37, their average being +2.80. Their 154 offspring range from +0.75 to +3.75, mean +2.46, a regression of 0.34. The parents of the last generation in this experiment, F, Table 49, were of mean grade plus 3.08. They produced 45 offspring of mean grade plus 2.67, a regression of 0.41. As a result of a single cross with a wild race followed by 6 successive selections, a narrow-striped or minus family has thus been converted into a wide-striped or plus family. Considering the smaller number of offspring from which selections could be made, progress was quite as rapid in this series as in the larger plus selection series. The regression is surprisingly similar, generation by generation, in the two series. See Table B. But it seems improbable that the closeness of the agreement has any significance. This series has the theoretical advantage of being derived from a single individual of the minus selection series. Crosses of the plus race with the minus race. When animals of the plus selection series are crossed with animals of the minus selection series, an F generation of offspring is obtained which varies about a mean intermediate between those of the respective uncrossed races. Thus, from an examination of Table 50 it will be seen that when -2 animals of generation 6, minus series, were crossed with plus 3.50 or plus 3.75 animals of generation 5, plus series, an F generation, series 1, was obtained consisting of 93 animals of mean grade plus 0.06. This generation is rather more variable than either uncrossed race, its standard deviation being 0.71. The same is true of a second set, series 2, of crosses made between a male of grade -3.25, generation 10, minus series, and females of grade plus 3.75, generation 10, plus series. The 14 F offspring are of mean grade plus 1 and have a standard deviation of 0.60. See Table 50. Series 2. In both the series of crosses summarized in Table 50, the F generation is more variable than F. In Series 1, 305 F animals are recorded, having a standard deviation of 1.01 as compared with 0.71, the standard deviation of the F generation. In Series 2, the F offspring number 73 and have a standard deviation of 0.87, that of the previous generation being 0.60. The mean of the F generation is very similar to that of the F generation. In Series 1, the mean of F is 0.06. and that of F is 0.24. In Series 2, the mean of F is 1.00, and that of F is 0.72. It may also be seen from an examination of Table 50 that among the F offspring produced by crossing the plus and the minus series there are differences in transmission, as there are in the expression of the hooded pattern. In general, those F individuals which are of high grade produce offspring of higher grade than do their low grade brothers and sisters. This is exactly what has been observed in both uncrossed races. Summary of results. The experiments which have been described in the foregoing pages have shown that, 1. The hooded pattern of rats behaves as a simple Mendelian character in crosses with either the Irish pattern or the wholly pigment condition of wild rats. 2. Though behaving as a unit, the hooded pattern fluctuates, that is, it is subject to plus and minus variations. 3. Selection, plus or minus, changes the position of the mean and mode about which variation occurs. 4. The results of such plus or minus selections are permanent, for return selection is not more effective than the original selection, and during return selection regression occurs away from the original mode, that is, toward the mode established by selection. 5. During the progress of the original selection, 13 successive generations, variability as measured by the standard deviation was somewhat diminished. 6. Upon crossing the selected plus and minus races with each other, the variability was somewhat increased in F and was further increased in F. The extreme conditions, plus or minus, of the grandparents rarely, if ever, recur in this generation. Only one individual among 378 F young has been recorded in a grade as extreme as either grandparent. 7. Hooded animals extracted in F as recessives from a cross with either Irish or wild rats are as a rule more variable than the selected race used in making the cross. In crosses with an Irish race the minus series was affected in like measure. In crosses with wild rats the variability of the plus series was not appreciably affected. In 2 experiments it was slightly reduced, and in 1 experiment it was slightly increased. But the variability of the minus race was more than doubled by crosses with wild rats. 8. The mean of the minus race was lowered by a cross with either the Irish race or with wild rats, but more extensively by the latter. The mean of the plus race was lowered a very little by a cross with wild rats, but considerably by a cross with the Irish race. Discussion. It would be possible to suppose, as the senior author has elsewhere suggested, Castle, 1912, that the Mendelian unit character involved in these experiments is subject to quantitative variation and that such quantitative variations have a tendency to persist from generation to generation. This would account for the effectiveness and permanency of selection when brought to bear upon the variations. It might also form a basis for explaining the increased variability which follows crossing, this being regarded as due to contamination in the heterozygote, but there are certain other observed effects of crossing which it seems impossible to account for on this basis. In particular, it is observed that while crossing the minus series makes it less minus as the hypothesis of contamination would demand, crossing the plus series makes it less plus, the opposite of what a contamination theory would demand. For we can readily understand, on the basis of contamination, how a +6 gamete being combined with a -2 gamete might change the latter in a plus direction, but if the same +6 gamete is associated with a +4 gamete we should expect it, if it has any influence at all, to make this also more plus, but the observed effect is the opposite, the extracted gametes are less plus in character. This difficulty is met by an alternative explanation, the main feature of which was first suggested by our colleague, Drem East, viz., that although we seem to be dealing with a single unit character as evidenced by the monohybrid ratios obtained, nevertheless the modifications which form a basis for selection are due, in part at least, to agencies transmitted independently of the hooded pattern, not forming a part of the same unit character, and which may be present in Irish as well as in wild rats. By crosses with such rats the supposed modifiers may become associated with the hooded pattern in extracted recessive individuals and so increase its extent. Such increase does actually occur in experiment. The hypothesis of modifiers independent in transmission of the hooded unit will account for the fact that F is more variable than F when crosses are made, on the familiar principle of recombination of independent factors. It will account for the observed effectiveness of selection on the ground that what selection accomplishes in the plus series is the isolation of homozygous conditions of modifiers at first present only in heterozygous form, and that what it accomplishes in the minus series is the isolation of conditions homozygous for lack of modifiers, or for inhibitors, of pigmentation. This same hypothesis will account also for the observed reduction of variability during the progress of selection, for as soon as any particular modifier attains a homozygous condition in the race it will cease to occasion variability, and as more and more factors become homozygous the variability should accordingly diminish and finally disappear altogether, so far as it is due to internal and heritable causes. At this point the hypothesis of modifiers encounters serious difficulty, if one holds the prevalent or genotype conception as to the nature of Mendelian factors, viz., that they are fixed and unchangeable and not subject to quantitative variation, but only to combination in different ways with other factors. This conception has been presented very clearly by Dr. East, 1912. Some objections to this view had previously been stated by Castle, 1912, and need not here be repeated. If we assume that there exists at the outset a definite number of modifiers and that these possess a definite and unchanging power to modify, then it is evident that selection can do nothing but secure homozygous conditions as regards the presence or absence of these modifiers. When such homozygous conditions are secured, selection will cease to modify the race. The experiment has progressed far enough to show that extensive modification through selection is possible without any marked falling off in variability. No indication is observable that selection will become ineffective before an all-black rat is obtained in the plus series and an all-white rat in the minus series. A nearly all-black race of rats has already been secured. We propose to continue the experiments until demonstrative evidence is obtained. If the fixed factor idea as regards modifiers of the hooded pattern is rejected, there remain still two possible alternative views regarding them. Either we may consider that the modifiers vary in strength, that is, in power to modify, or we may consider that new modifiers arise from time to time, which selection may either add in homozygous form to the germinal complex or reject altogether from it. If we assume that the modifiers vary in strength, we shall have to grant also the possibility that the character modified, the hooded pattern, may itself vary in strength independently of its modifiers. For evidence see the description of the mutant series, page 30. This assumption, I understand, would be unacceptable to those who hold a genotype conception of heredity, though we ourselves can offer no valid objection to it. If, on the other hand, we admit that new modifiers or inhibitors are from time to time coming into existence spontaneously, and that selection can use these to modify the pattern either in a plus or in a minus direction, then we must admit that selection is an agency of real creative power, able to modify unit characters indefinitely so long as physiological limitations are not reached. Now it seems to us probable that what we call the unit character for hooded pattern is itself variable, also that modifiers exist, that is, the extent of the hooded pattern is not controlled exclusively by a single localized portion of the germ cell, otherwise we should be at a loss for an explanation of the peculiar results from crossing plus series hooded rats with those which are still more extensively pigment, for by such crosses the pigmentation is rendered not more extensive but less. So, this result we can explain on the supposition that the selected plus series has accumulated more modifiers of the hooded pattern than the wild race contains, so that a cross tends to reduce the number of modifiers in the extracted hooded individuals. No other explanation at present offers itself for this wholly unexpected but indubitable result. If a different one can be found, we are quite ready to discard the hypothetical modifiers as a needless complication, contenting ourselves with the supposition that the unit character for hooded pattern is itself variable, and that for this reason racial change in either plus or minus directions may be secured at will through repeated selection. We have been led to adopt tentatively an hypothesis that modifying factors exist independent of the single factor for hooded pattern, though both the factor for hooded pattern and its modifiers may, so far as we can see, be quantitatively variable, by another series of observations, which will now be described. The mutant series. In the 10th generation of the plus selection series there appeared two individuals, a male and a female, of considerably higher grade than any previously recorded in this series. They are not included in Table 10 because we have been and still are in doubt as to their exact nature and think it best to give a separate account of them. If entered in Table 10, one would appear as a 5½ individual born of 3 7/8 parents, mean grade, the other as a 5 3/4 individual born of 3 3/4 parents, mean grade. The nearest individuals in grade to these two produced by the same group of parents are of grade 4½. But some 4 1/8 parents of the same generation produced two offspring of grade 5. See Table 10. Because of the marked advance in grade of these individuals beyond the ordinary range of variation in the series, we called them mutants without wishing then or now to commit ourselves to any particular theory as to their nature or origin. We have used the term and now use it as one of convenience merely. The two mutant individuals had the same father and their mothers were sisters. Their pedigree for 2 generations is as follows: mutants, parents, grandparents. Male sign 4763. Plus 5 1/2, female sign 2956, plus 3¾ female sign 1939, plus 3¾ female sign 2957, plus 3½ male sign 1817, plus 3¾ female sign 5153, plus 5¾ female sign 1162, plus 3½ male sign 2963, plus 4 male sign 1810, plus 3¾ the mutant male was mated with the mutant female and also with other females of the plus series, with the results shown in Table 51. In every case the young fall into two distinct groups, one of which varies about the general mean of the plus series, approximately 3 3/4, while the other varies about the father's grade as a mean, approximately 5 1/2. The mutant female had 16 young, 6 in the lower group, mean 3.87, and 10 in the upper group, mean 5.60. See Table 51, lowest row. The other females had in all 114 young, almost equally divided between the two groups, 58 in the lower group, mean 3.73, and 56 in the upper group, mean 5.45. This result indicates clearly, what the sequel also confirms, that the male mutant transmitted in half his gamete is the high grade of pigmentation which he himself manifested, while in the other half of his gametes he transmitted the ordinary condition of the plus race at that time. In other words, his mutant character behaved as a dominant unit in relation to the ordinary condition of the plus race. It is evident that the female mutant was of similar constitution. This being the case, we should expect 3/4 of the offspring of the two mutants to be in the upper group. In reality 10 of their 16 young were of this sort. The male mutant was mated also with females of the minus series with the results indicated in Table 52. Again, the offspring fall into two distinct groups, a lower and an upper. The lower group should be comparable with the result obtained in F when the plus and minus races are crossed with each other. Compare Table 50. Such it proves to be. It includes 35 individuals of mean grade minus 0.49 and standard deviation 0.77. Series 2 of Table 50 is nearly contemporaneous with this experiment. The F offspring in that series were of mean grade minus 1 and standard deviation 0.60. The upper group of offspring, Table 52, result, we may suppose, from a mutant gamete, grade about 5 1/2, united with a narrow series gamete, grade about minus 2. This group includes 31 individuals varying closely about grade 4 1/2, and with a standard deviation of only 0.31. The lower average grade of this group, 4.43, compared with the similar group of Table 51, which had a mean of 5.47, shows the influence of the minus series gamete upon the heterozygote in lowering its grade by about 1. Whether the plus series gametes have any effect upon the grade of the heterozygotes recorded in the upper group of Table 51 is not certain, because a homozygous group of mutants has not yet been established. It may be observed, however, that one individual in the upper group of Table 51 was of grade 6, colored all over, and it is possible that homozygous mutants, when obtained, will approximate that grade, as most wild rats do. Further, a comparison of tables 51 and 53 shows that mutant heterozygotes formed by crosses with the plus series are of slightly lower mean grade than the offspring of the two mutants, among which should occur both homozygous and heterozygous mutants. It seems probable, therefore, that homozygous mutants will be found to be of somewhat higher grade than heterozygous ones. The question early suggested itself to our minds: will these mutants prove to be mutants in the sense of de Vries? Will they prove to be more stable than the modifications ordinarily secured by selection in our experiments? To test this matter, we have raised 2 additional generations of offspring from the 2 mutants and have bred a second generation of offspring from each of the 4 groups of F offspring recorded in tables 51 and 52, derived from matings with the plus and minus races respectively. The F descendants of the 2 original mutants proved very similar to the F descendants. See Table 53. They fall as before into 2 groups, an upper and a lower. The former includes 30 individuals of mean grade 5.52, the latter 2 of mean grade 3.37. As the parents of this generation were taken wholly from the upper group of offspring of generation F, and as theoretically that group should contain 2 heterozygous individuals to one which is homozygous for the mutant character, it is to be expected that in F more than 3/4 of the offspring will fall in the upper group. For any pair, one member of which is homozygous for the mutant character, should produce only offspring falling in the upper group, and offspring falling in the lower group should be produced only by pairs both members of which are heterozygous. The upper group in F should contain a larger proportion of homozygous mutants than in F, and since the parents of F were chosen from this upper group of F offspring, it is not surprising that the 11 F offspring recorded up to this time all fall in the upper group. The mean of this upper group is remarkably constant through the 3 generations, and the variability of the group as measured by its standard deviation is also low, namely, 0.19. This indicates that the mutant character is a strongly dominant unit in relation to the ordinary condition of the plus series. Table 54 shows the character of the F offspring of the original male mutant mated with females of the plus series. The lower group parents, those into which the mutant character did not presumably enter at all, produced 59 offspring recorded in the first part of Table 54. Their mean grade is 3.78 and their standard deviation 0.33. These are very close to the constants of the general plus series, which for generation 10 were 3.73 and 0.36, respectively. The second division of Table 54 shows the character of the young produced by the F parents of the upper group, Table 51. Such parents are supposed to have received a mutant gamete from their father, grade about 5.50, and a plus series gamete from their mother, grade about 3.75. If they produce gametes of these same two sorts, their offspring should also fall into two corresponding groups. In fact, they do. There are 11 offspring of mean grade 3.86 and 79 offspring of mean grade 5.50. As in the previous generation, the two groups do not approach each other in grade. The mean and standard deviation of the lower group of offspring are similar to those of the plus race. The mean of the upper group is about the same as that of their parents' upper group of offspring, Table 51, namely, 5.50, as compared with 5.45. Their standard deviation is somewhat lower, namely, 0.15, as compared with 0.23. This result indicates that the mutant character and the hooded character of the plus series segregate from each other in a simple way without modifying each other appreciably. It seems possible that they contain the same modifiers, if modifiers are present, and differ merely by the main unit which we called the hooded character in the early part of this paper. Each contains a different condition of that main unit. Consequently, there is no increase of variability in F when these two conditions are intercrossed. This we should expect to happen, if they differed by more than a single factor. A very different result is obtained from the cross between the mutant and narrow races. Although F from that cross was quite variable, see Table 52, F is still more variable, see Table 55. The lower group F individuals, which resembled F between the plus and minus races, produced 61 young, first division of Table 55, which resemble F between the plus and minus races. They range in grade from -2 to +3 1/4, mean +0.58, standard deviation 1.17. In the two series of crosses between the plus and minus races, Table 50, the means were +0.24 and +0.72, respectively, and the standard deviations 1.01 and 0.87. This indicates, as did the cross with the plus series, that the lower group gametes produced by the original mutant male did not differ materially from gametes produced by the ordinary plus race from which the mutant sprang. The second division of Table 55 shows the character of the F young produced by the upper group of F offspring recorded in Table 52. It consists of two groups, a lower and an upper. The lower represents the extracted minus race, the upper represents the extracted dominants or mutants, whether homozygous or heterozygous. The former group has an average of +0.75 and a standard deviation of 1.03, which values are close to the corresponding constants of Series 2, Table 50, the latest of the plus-minus crosses, in which the mean was +0.72 and the standard deviation 0.87. The upper group offspring of Table 55, second division, the homozygous and heterozygous mutants, number 68. they have a mean grade of 4.77 as compared with 4.43 in F, which consisted exclusively of heterozygotes. This shows the extracted homozygotes to be of higher grade than the heterozygotes. The highest grade mutant among the 31 F young, all of which were heterozygotes, was of grade 5, but among the 68 F young are 16 of higher grade than 5. We expect 1/3 of these 68 individuals to be homozygotes. Now all of the F mutants from the cross of mutant with plus race, Table 54, were of grade 5 or higher, only 2 in 79 being as low as 5, and 13 of the 79 being of grade 5 3/4, a grade not attained at all in F from the mutant minus cross, Table 55. This result shows us that the cross with the minus race does affect permanently the mutant character, lowering its grade even in homozygous mutants extracted from the cross. It also increases the variability of the mutants, for the standard deviation of the mutant group in Table 55 is 0.44, whereas in Table 54, mutant plus F, in a like number of individuals, it was 0.15, or only about 1/3 as great. That the variability of the mutants is unaffected by a cross with the plus race, but that it is increased by a cross with the minus race, and that, further, the mean of the mutants is affected little or none by a cross with the plus race, but that it is lowered by a cross with the minus race. These several facts are all conformable with the hypothesis that the change in variability due either to crossing or to selection results from modifying factors which, as they are independent of the main factor concerned, are probably transmitted in a different part or component of the germ cell than that factor. For if the mutant and the plus race are alike as regards the modifiers, but differ only in the main factor, then no change in variability should result from intercrossing them, but only alternative conditions as regards the main factor. This is the observed result. But if the mutant and the minus race differ not only in the main factor, but also in modifiers which are independent of it, then, when they are crossed, we may expect that through independent segregation of main factor and modifiers the extracted minus race will be raised in grade, while the extracted mutants are lowered, and both will become more variable. This also is the observed result. One objection may be offered to this interpretation, namely, that the increased variability is not delayed until F, but is already in evidence to some extent in F. The same thing was observable in the crosses of the plus and minus series, Table 50. From that table, Series 1, it will be observed that when the plus and minus races had standard deviations of 0.49 and 0.50, respectively, their F offspring had a standard deviation of 0.71, an increase by nearly 1/2. F showed a further increase to 1.01. In Series 2, Table 50, the uncrossed races, Generation 10, had standard deviations of 0.36 and 0.24. Their F offspring had a standard deviation of practically twice this, namely 0.60. F showed a further increase to 0.87. At the time of the mutant minus race crosses, the minus race, generation 10, had a standard deviation of 0.24, the plus race of 0.36. F, lower group, had a standard deviation of 0.77, and F of 1.17. F mutants, upper group, had a standard deviation of 0.31 which rose in F to 0.44. These various facts will perhaps be better grasped if presented in tabular form. Table C. Standard deviation of races crossed, same generation. SDF plus minus cross, Series 1, Table 50, 0.49 0.50 0.711 0.01 plus minus cross, Series 2, Table 50. 36.24.60.87 mutant minus cross, lower group. 25.24.77 1.17 mutant minus cross, upper group. 19.24.31.44 mutant plus cross, lower group. 25.36.24.35 mutant plus cross, upper group. 19.36.23.15 The mutant plus cross, it will be observed, shows no increase of variability either in F or in F, but crosses involving the minus race show increase of variability both in F and in F. Interpreted on a Mendelian basis, this means that the mutant and plus races on the one hand and the minus race on the other hand differ by more than a single factor. If they differed by only a single factor, then crosses between them should bring no increase of variability, either in F or in F. This appears to be true as regards the mutant and plus races when crossed with each other. But if the races crossed differ by more than one factor, and if, further, neither parent is homozygous as regards the factors in which they differ, then we may expect an increase in variability both in F and in F. This is exactly what we observe when the minus race is crossed with either the plus race or its derivative, the mutant race. If we suppose that the plus race and the minus race differ from each other by certain modifiers, we cannot suppose that the plus and the mutant races differ by these same modifiers. They differ in some other single respect, perhaps that in which they differ is the main hooded factor. Are we, then, to suppose that the plus and the minus races do not differ as regards this same main factor? This cannot be stated, but we see no reason for considering them identical as regards that factor. It appears that the mutant race arose from the plus race by a single large plus variation, which seems to have its determiner in some single component of the germ cell. But the fact that this change came as a large quantitative variation does not show that small variations are impossible in that same cell component. It seems to us quite improbable that the plus mutation could have arisen in the minus selection series. We believe that the repeated selection which was practiced had something to do with inducing this change in the plus direction. If one can increase at will the modifiers which make the pigmentation more extensive, It does not seem strange that after a time a readjustment should occur within the cell which should incorporate modifiers in that part of the cell which is responsible for the unit character behavior of the hooded pattern. This would amount to a quantitative change in the unit character for hooded pigmentation. Bibliography. Castle, W.E. 1905. Heredity of Coat Characters in Guinea Pigs and Rabbits. Caen. Inst. Wash. Pub. 23 1906. The Origin of a Polydactylous Race of Guinea Pigs. Caen. Inst. Wash. Pub. 49 1912. The Inconstancy of Unit Characters. American Naturalist, Volume 46, pp. 352 to 362. Castle, W.E., and Alexander Forbes. 1906. Heredity of hair length in guinea pigs and its bearing on the theory of pure gametes. Caen. Inst. Wash. Pub. 49. De Vries, H. 1901–1903. Diamutations Theory. Vita and Company, Leipzig. East, E.M. 1912. The Mendelian Notation as a Description of Physiological Facts. American Naturalist, Volume 46, pp. 633 to 655. Jennings, H.S. 1909. Heredity and Variation in the Simplest Organisms. American Naturalist, Volume 43, pp. 321 to 337. 1910. Experimental Evidence on the Effectiveness of Selection. American Naturalist, Volume 44, pp. 136 to 145. Johansen, W. 1909. Element der exakten Urblichkeitslehre. G. Fisher, Jana. McCurdy, H., and W. E. Castle. 1907. Selection and crossbreeding in relation to the inheritance of coat pigments and coat patterns in rats and guinea pigs. Caen. Inst. Wash. Pub. 70. Pearl, R. 1913. Genetics and Breeding. Science, N.S., Volume 37, pp. 539 to 546. Tables. Table 1. Classification of the first generation of offspring in the Plus selection series. At the head of each column is indicated the grade of the individuals recorded in that column. The figures in the body of the table indicate the numbers of offspring of the several grades indicated. Grade of parents. Grade of offspring. Totals. Means. Regression. +1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 1 7/8 1 1 1 1 1 1 1 7 1.82.0524 13141 18 1.76.24 2 1/8 2 1/4 3 1 3 1 6 2 22 21.87.38 2 3/8 2 1/2 5 3 1 13 185 137 2.06.44 2 5/8 1 1 2 1 5 2.15.47 2 3/4 7 3 2 17 1 12 9 51 2.12.63 2 7/8 3 2 3 1 3 3 12 2.35.65 totals or means 2.51 23 13 8 44 7 31 10 4 152.05.46 Table 2. Classification of offspring in Generation 2 plus Selection Series. Grade of parents. Grade of offspring. Totals. Means. Regression. -1 3/4 1/2 1/4 0 plus 1/4 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 2 1 1 4 2 5 7 3 7 8 2 3 2 1 46 1.70 0.32 1/8 1 1 2 1 3 5 12 8 5 5 8 2 1 2 56 1.28.82 2 1/4 1 1 3 1 1 1 8 1.87.38 2 3/8 1 1 4 9 7 8 86 145 1.92.45 2 1/2 4 22 16 19 11 21 13 7 10 9 1 133 1.80.72 5/8 1 2 3 1 6 5 7 9 6 3 1 44 2.11.51 2 3/4 1 3 4 2 6 5 9 6 9 6 1 52 1.92.83 2 7/8 1 1 3 5 3 9 1 23 2.41.46 3 1 2 3 2 14 7 4 5 11 6 3 1 59 2.47.53 3 1/2 2 1 2 5 2.50.62 totals or means 2.521 to 214 15 16 45 37 45 45 77 57 44 48 39 31 471 1.92.60 Table 3. Classification of offspring in Generation 3 plus Selection Series. Grade of parents. Grade of offspring. Totals. Means. Regression. 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 4 2 1/8 1 1 5 6 4 1 3 21 2.06.06 2 1/4 2 3/8 5 5 1 4 2 17 2.15.22 2 1/2 1 2 1 2 5 5 10 10 9 7 2 54 2.32.18 2 5/8 2 1 3 9 4 5 15 18 3 1 2 1 64 2.64.02 2 3/4 2 1 7 10 7 7 7 1 1 40 23 2.46.29 2 and 7/8 1737 9 10 9 147 2.70.17 3 2 1 12 14 11 17 11 3 71 2.49.51 3 and 1/8 2 5 1 2 10 3.07.05 3 and a quarter 1 2 1 2 6 3.17.08 3 and 3/8 2 1 3 2 8 2.91.46 totals or means 2.731258 20 51 46 47 66 63 21 641 341 2.51.22 Table 4. Classification of offspring, Generation 4, plus Selection Series. Grade of parents. Grade of offspring. Totals. Means. Regression. 3/4 1 1 and a quarter 1 and a half 1 and 3/4 2 2 and a quarter 2 and a half 2 and 3/4 3 3 and a quarter 3 and a half 3 and 3/4 2 and a half 2 2 4 3 11 2.55.05 2 and 5/8 2 and 3/4 3 3 2 3 4 3 18 2.65 10 2 and 7/8 1 3 3 7 15 4 3 2 37 2.97 10 3 1 1 7 12 25 19 35 29 9 4 1 143 2.60 43 and 1/8 1 2 11 14 21 28 30 11 2 2 122 2.69.43 3 and a quarter 1 168 13 17 9 8 164 2.89.36 3 and 3/8 16 2 9 223 2.70.67 3 and a half 3 1 2 3 6 2 3 23.02 2.48 3 and 5/8 3 and 3/4 3 1 1 1 6 2.751.00 totals or means 3.091112 12 30 60 58 96 110 45 199 444 2.73.36 Table 5. Classification of Generation 5 plus Selection Series. Grade of parents. Grade of offspring. Totals. Means. Regression. 3/4 1 1 and a quarter 1 and a half 1 and 3/4 2 2 and a quarter 2 and a half 2 and 3/4 3 3 and a quarter 3 and a half 3 and 3/4 4 4 and a quarter 2 and 3/4 1 2 4 4 1 12 3.00.25 2 and 7/8 4 4 4 2 3 2 2 21 2.8703153231 15 2.81.19 3 and 1/8 11118 14 20 29 18 831 114 2.81.31 3 and a quarter 1114 12 6 14 24 39 27 7 1 1 138 2.81.44 3 and 3/8 115 14 11 25 36 28 15 7 to 145 2.94.43 3 and a half 6 5 10 14 16 8 8 3 69 2.86.64 3 and 5/8 3 3 5 7 16 12 11 4 3 64 3.08.54 3 and 3/4 2 2 4 3 2 1 14 3.07.68 3 and 7/8 1 1 1 1 2 2 8 3.35.52 4 1 1 1 1 2 1 7 3.36.64 4 and 1/8 1 1 1 3 3.001.12 totals or means 3.33122226 35 44 66 101 151 107 57 24 11 1610 2.90 43 Table 6. Classification of Generation 6 plus Selection Series. Grade of Parents. Grade of Offspring. Totals. Means. Regression. 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 4 4 1/4 4 1/2 3 1 1 2 3 1/8 3 4 1 1 4 7 5 3 28 2.84.28 3 1/4 1 3 3 8 26 31 31 24 15 1 143 3.10.15 3 and 3/8 1 5 6 13 20 28 30 14 5 123 2.96.41 3 1/2 1 9 4 15 29 49 41 43 17 4 212 3.10.43 and 5/8 4 8 11 24 34 36 37 21 5 1 181 3.16.46 3 and 3/4 1 1 2 1 3 4 18 13 20 13 278 3.22.53 3 and 7/8 4 1 3 5 14 15 20 14 483.26.61 4 1 2 1 5 4 1 14 3.41.59 totals or means 3.5235 32 24 54 113 183 172 166 90 171 861 3.11.41 Table 7. Classification of Generation 7 plus Selection Series. Grade of Parents. Grade of Offspring. Totals. Means. Regression. 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 4 4 1/4 4 1/2 4 3/4 3 1/8 2 2 4 5 7 4 3 1 28 2.87.25 3 1/4 1 6 11 7 11 30 19 22 23 1 131 3.09. 16 3 and 3/8 1 2 10 18 17 21 27 18 21 24 1 162.97. 43 and a half 6 9 9 21 31 28 35 34 3 1 177 3.18. 32 3 and 5/8 7 11 13 26 47 53 75 49 7 1 289 3.23. 39 3 and 3/4 2 3 3 16 28 25 58 42 4 3 184 3.35. 43 and 7/8 2 1 2 4 10 12 23 21 6 6 2 193.49. 38 4 1 1 3 2 4 3 1 15 3.53. 47 4 and 1/8 1 1 1 3 3.75. 50 totals or means 3.5622 35 55 56 105 183 159 241 95 29 1222 1077 3.20. 36 Table 8. Classification of Generation 8 Plus Series. Grade of Parents. Grade of Offspring. Totals. Means. Regression. 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 4 4 1/4 4 1/2 3 1/4 2 2 4 3.25 3 3/8 3 1/2 1 4 6 9 18 17 2 2 59 3.46. 0 4 3 and 5/8 1 2 9 13 30 69 44 144 149 22 1 484 3.50. 12 3 and 3/4 2 1 9 12 55 39 152 173 23 2 469 3.49. 26 3 and 7/8 1 2 4 23 18 98 69 19 2 1 238 3.53. 34 4 1 2 3 10 6 34 6 1 164 3.31. 69 4 and 1/8 2 5 2 14 13 14 10 63.72. 44 1/4 1 7 11 2 1 22 3.69. 56 4 and 3/8 2 5 1 3.96. 41 totals or means 3.75 15 13 25 55 170 119 469 440 88 201 1408 3.48. 27 Table 9. Classification of Generation 9 Plus Series. Grade of Parents. Grade of Offspring. Totals. Means. Regression. 1 3/4, 2 2 1/4, 2 1/2, 2 3/4, 3 3 1/4, 3 1/2, 3 3/4, 4 4 1/4, 4 1/2, 3 1/2, 1 1 1 1 4 3.25.25, 3 5/8, 1 1 6 12 28 26 96 63 10 1 244 3.43.19, 3 3/4, 1 247 1945 50 224 212 25 2 591 3.50.25, 3 7/8, 2 525 32 105 177 64 86 424 3.65.22 4125 14 15 7 145 3.57.43 4 1/8 2 417 3.57.55 4 1/4 1 124 3.75.54 3/8 333.50.87 totals or means 3.78 17 38 105 110 443 473 109 11 7 1322 3.54.24 Table 10. Classification of Generation 10 plus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 2 1/4, 2 1/2, 2 3/4, 3 3 1/4, 3 1/2, 3 3/4, 4 4 1/4, 4 1/2, 5 3 3/4, 1 19 13 63 117 44 8 1 257 3.69.06 3 7/8, 1 3 16 95 142 62 205 347 3.72.15 44 26 61 27 2 123.76.24 4 1/8 11 17 7 6 1 244 3.87.25 4 1/4 1 4 2 1/8 3.84.41 totals or means 3.88 1 1 4 12 33 196 341 135 42 92 776 3.73.15 Table 11. Classification of Generation 11 plus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 2 3/4, 3 3 1/4, 3 1/2, 3 3/4, 4 4 1/4, 4 1/2, 4 3/4, 5 3 3/4, 2 7 2 11 3.750 3 7/8, 2 7 17 87 162 41 1133 333 3.70.17 432 25 87 65 24 611 214 3.87.13 4 1/8 33 16 49 27 822 110 3.81.31 4 1/4 1/4 2 13 5 3 1 1 25 3.91.34 4 3/8 1 3 4 3.94.43 totals or means 3.97 13 22 132 319 143 46 127 697 3.78.19 Table 12. Classification of Generation 12 plus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 2.5 3 3.25 3.5 3 3/4 4 4.25 4.5 4 3/4 5 5.25 3 3/4 4 27 4 35 3.83.083 7/8 2 19 17 6 22 48 3.96.094 1 1 10 53 59 12 5 1 1 2 145 3.93.074 and 1/8 1 2 17 86 83 28 6 3 1 227 3.91.21 4.25 1 7 19 29 11 3 1 71 3.94.31 4 3/8 3 6 14 10 7 3 1 1 45 4.13.24 4.5 1 4 1 1 7 4.14.36 4 5/8 1 3 4 3 11 3.90.72 5 1 1 4.75.25 totals or means 4.0913 43 207 217 75 23 11 43 593.94.17 Table 13. Classification of Generation 13 plus Selection Series. Grade of parents. Grade of offspring. Totals. Means. Regression. 2 3/4 3.25 3.5 3 3/4 4 4.25 4.5 4 3/4 4 4 17 23 19 265 3.67.31 4 1/8 1/8 16 5 131 3.97.15 4.25 1 5 10 26 143 3.93.32 4 3/8 1 5 3 1 10 3.85.52 4.5 1 14 15 7 3 43.98.52 4 5/8 3 1 1 5 3.95.80 totals or means 4.2214 25 63 74 21 5 1 194 3.88.34 Table 14. Summary of the results of 13 generations of plus selection based on tables 1 to 13. Generation. No of offspring. Mean, parents. Mean, offspring. Standard deviation, parents. Standard deviation, offspring. Correlation, parents-offspring. Absolute regression of offspring on parents. Advance of parents. Advance of offspring. Total 8,941. Table 15. Mean grade and number of offspring produced by parents of a particular grade in each generation of the Plus Selection series, based on tables 1 to 13. The grade of the parents is indicated at the head of each column. In the body of the table is recorded the grade of the offspring, in light-faced figures, and the number of offspring, in heavy-faced figures. Generation. Grade of parents, below, grade and number of their offspring. Total number of offspring. 2 2 1/8, 2 1/4, 2 3/8, 2 1/2, 2 5/8, 2 3/4, 2 7/8, 3 3 1/8, 3 1/4, 3 3/8, 3 1/2, 3 5/8, 3 3/4, 3 7/8, 4 4 1/8, 4 1/4, 4 3/8, 4 1/2, 4 5/8, 4 2.76 1.87 2.06 2.15 2.12 2.35 18 20 37 5 51 12 2 1.70 1.28 1.87 1.92 1.80 2.11 1.92 2.41 2.47 2.50 46 56 8 45 133 44 5 2 23 59 5 3 2.06 2.15 2.32 2.63 2.46 2.70 2.49 3.07 3.17 2.91 21 17 54 64 43 47 71 10 6 8 4 2.55 2.65 2.97 2.60 2.69 2.89 2.70 3.02 2.75 11 18 37 143 122 64 2 3 26 5 3.00 2.87 2.81 2.81 2.81 2.94 2.87 3.08 3.07 3.35 3.36 3.00 12 21 15 114 138 145 69 64 14 87 36 3.25 2.84 3.10 2.96 3.10 3.16 3.22 3.26 3.412 28 143 123 212 181 78 80 14 7 2.87 3.09 2.97 3.18 3.23 3.35 3.49 3.53 3.75 28 131 160 177 289 184 90 153 1077 83.46 3.50 3.49 3.53 3.31 3.72 3.69 3.96 59 484 469 238 64 60 22 8 1408 9 3.25 3.43 3.50 3.65 3.57 3.57 3.75 3.504 244 591 424 45 743 1322 10 3.69 3.72 3.76 3.87 3.84 257 347 120 44 8 776 11 3.75 3.70 3.80 3.87, 3.81, 3.91, 3.94, 11, 333, 214, 110, 25, 4, 697, 12, 3.82, 3.96, 3.93, 3.91, 3.94, 4.12, 4.14, 3.90, 4.75, 35, 48, 145, 227, 71, 457, 11, 1, 590, 13, 3.67, 3.97, 3.93, 3.85, 3.98, 3.95, 65, 31, 43, 10, 45, 194. 8941. Table 16. Classification of the offspring in Generation 1 of the minus selection series. Grade of parents. Grade of offspring. Totals. Means. Regression. Plus 1/4, 0 1/4, 1/2, 3/4, 1 1 1/4, 1 1/2, 1 3/4, 2-1 1/4, 1 2 3 2 8 1.34.09 1 3/8, 1 1 3 12 8 3 1 1 1 31.86.51 1 1/2 1 1 1 1 1 1 6 1.37.13 1 7/8 1 1 2 2 3 1 10 1.05.82 Totals or means 1.462141 15 13 485 255 1.00.46 Table 17. Classification of Generation 2 minus selection series. Grade of parents. Grade of offspring. Totals. Means. Regression. Plus 1/2, 0 1/4, 1/2, 3/4, 1 1 1/4, 1 1/2, 1 3/4, 2 3/4, 1 2 2 1 6 2 3 2 19 1.04.29 1 1/8 2 2 2 2 3 1 12 1.05.07 1 1/4 4 6 3 3 1 17 1.18.07 1 3/8 1 1 1 2 5 1.45.08 1 1/2 1 10 13 1 8 4 37 1.11.39 1 5/8 1 1 1 3.67.95 1 3/4 1 1 2 14 4 3 1 1 27 1.09.66 1 7/8 1 1 1 2 3 1 3 12 1.10.77 Totals or means 1.412366 20 44 13 19 14 5 132 1.07.34 Table 18. Classification of Generation 3 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/4, 1/2, 3/4, 1 1 1/4, 1 1/2, 1 3/4, 2-1 2 1 1 1 5.85.27 1 1/4 1 3 6 5 1 2 1 1 21.05.21 3/8 1 3 4 11 3 4 2 28 1.03.34 4 1 and a half 1 1 12 1 5 5 3 28 1.31.19 1 and 5/8 1 1 1 10 10 5 8 8 4 48 1.22.41 and 3/4 1 2 8 19 9 9 7 8 63 1.26.49 1 and 7/8 3 3 1.00.87 totals or means 1.56 14 12 30 61 19 29 23 16 195 1.18.38 Table 19. Classification of Generation 4 minus Selection Series. Grade of Parents. Grade of Offspring. Totals. Means. Regression. Plus 1/2 and 1/4 0 1/4 a half 3/4 1 1 and a quarter 1 and a half 1 and 3/4 2 2 and a quarter dash 1 1/4 1 1 1 1 4 1.56.31 1 and 3/8 2 3 4 8 3 1 2 6 29 1.16.21 1 and a half 1 1 3 2 7 7 6 8 16 8 59 1.31.19 1 and 5/8 1 4 10 4 8 7 6 41.36.26 1 and 3/4 4 4 6 19 11 16 22 11 93 1.34.41 1 and 7/8 2 1 2 6 1 10 19 12 17 19 5 1 95 1.18.69 2 1 2 3 1 2 9 1.36.64 Totals or means 1.6922 16 10 32 66 39 51 68 39 1 329 1.28.41 Table 20. Classification of Generation 5 minus Series. Grade of Parents. Grade of Offspring. Totals. Means. Regression. 0 1/4 a half 3/4 1 1 and a quarter 1 and a half 1 and 3/4 2 2 and a quarter 2 and a half 7/8 2 1 4 5 3 4 1 21.09.22 1 2 1 1 4.99.0 1 1 and 3/8 4 1 1 6 2 10 14 11 2 51 1.50.13 1 and a half 1 3 9 9 11 7 7 5 1 53 1.25.25 1 and 5/8 1 1 5 12 4 15 12 4 54 1.35.27 1 and 3/4 9 14 29 50 30 50 55 24 1 262 1.30.45 1 and 7/8 4 11 12 29 50 31 6 143 1.64.23 2 1 2 11 14 5 19 28 25 4 109 1.52.48 2 and 1/8 1 2 2 5 1.80.32 Totals or means 1.733 18 21 63 108 64 134 172 104 13 1701 1.41.32 Table 21. Classification of Generation 6 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/4 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 1 1 1 2 1 5.85.27 1 3/8 1 1 1 1 4 1.44.07 1 1/2 1 3 4 4 4 6 2 24 1.34. 16 1 5/8 1 1 11 16 3 17 28 17 94 1.45.17 1 3/4 1 1 8 14 39 20 39 77 43 2 244 1.49.26 1 7/8 1 9 24 61 40 71 156 127 12 1 502 1.59.28 2 1 3 5 12 32 22 37 89 76 5 1 283 1.58.42 2 and 1/8 2 4 4 5 35 31 485 1.52.62 1/2 2 5 3 1 11 1.82.68 totals or means 1.86 36 25 66 159 94 177 396 322 4 1252 1.56.30 Table 22. Classification of Generation 7 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/4 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 1 5/8 1 1 2 1 5 1.55.07 1 3/4 1 2 1 1 6 11 9 1 32 1.67.08 1 7/8 216 35 20 47 99 106 631 331.65.22 28 14 51 60 119 368 324 22 3 969 1.72.28 2 and 1/8 1 2 3 14 10 30 92 104 4 261.74.38 2 1/4 5 10 19 6 141 1.93.32 2 and 3/8 224 1.63.74 2 1/2 1 4 10 15 1.88.62 2 and 5/8 138 118 2.28.09 2 and 3/4 336 1.87.88 totals or means 2.0122 17 24 101 92 211 594 584 43 82 1681.73.28 Table 23. Classification of Generation 8 minus series. Grade of parents. Grade of offspring. Totals. means, regression. 0 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 1 7/8 198 119 1.84.03268 38 22 122 550 423 21 93 1202 1.81.19 2 1/8 13 12 7 31 118 187 32 23 396 1.86.26 2 1/4 1 2 19 23 45 1.87.38 2 3/8 1 1 11 17 31.87.52 1/2 3 6 15 4 28 1.93.57 2 5/8 3 2 1 6 1.67.95 totals or means 2.0516 11 52 30 162 715 671 61 116 1726 1.80.25 Table 24. Classification of generation 9 series. Grade of parents. Grade of offspring. Totals. Means. Regression. 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 2 1 13 4 36 268 420 55 104 811 1.90.10 2 1/8 1 125 110 218 47 1 403 1.93.19 2 1/4 1 17 43 77 12 6 1 148 1.93.32 2 3/8 1 17 61 89 12 4 175 1.91.46 2 1/2 126 23 14 5 253 2.07.43 2 5/8 1 12.00.62 totals or means 2.1111 16 7 77 488 828 133 32 8 1591 1.92.19 Table 25. Classification of generation 10 series. Grade of parents. Grade of offspring. Totals. Means. Regression. -1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 2 1 2 13 120 287 43 7 2 2 1 478 1.96.042 and 1/8 2 1 15 100 2 5 1 7 8 2241 474 2.00.12 2 and a quarter 545 92 58 13 4 217 2.05.22 and 3/8 1 4 16 60 29 6 3 119 2.05.32 2 and a half 9 27 19 10 267 2.13.37 2 and 5/8 1 5 17 17 8 149 2.15.47 2 and 3/4 1 18 10 6 127 1.95.82 and 7/8 1 1 2 3 6 5 2 22.19.68 totals or means 2.1836 4305 747 256 72 1732 1451 2.01.17 Table 26. Classification of Generation 11 series. Grade of parents. Grade of offspring. Totals. Means. Regression. -1 1 and a quarter 1 and a half 1 and 3/4 2 2 and a quarter 2 and a half 2 and 3/4 3 3 and a quarter 3 and a half 2 7 26 14 3 1 51 2.08.08 2 and 1/8 4 20 75 45 26 12 1 183 2.15.032 and a quarter 1 12 49 111 76 50 13 6 318 2.13.12 2 and 3/8 2 1 4 24 112 66 3 3 24 2 268 2.16.21 2 and a half 1 4 32 21 16 7 81 2.21.29 2 and 5/8 1 3 18 15 11 4 52 2.20.42 2 and 3/4 1 4 9 4 3 1 1 2 126 2.26.49 2 and 7/8 2 215 1.95.92 totals or means 2.3032 22 113 385 242 142 57 1251 984 2.15.15 Table 27. Classification of Generation 12 series. Grade of parents. Grade of offspring. Totals. Means. Regression. 1 1 and a half 1 and 3/4 2 2 and a quarter 2 and a half 2 and 3/4 3 3 and a quarter 3 and a half 2 2 7 110 1.98.022 and 1/8 1 6 65 26 15 4 1 118 2.14.022 and a quarter 1 2 16 67 45 29 6 155 2.15.10 2 and 3/8 121 116 6 4 2431 232.11.26 2.5 112 81 75 53 17 3 242 2.24.26 2 and 5/8 5 38 36 37 12 8 1 137 2.32.32 and 3/4 8 7 14 10 3 42 2.45.32 and 7/8 1 7 9 14 15 7 53 2.51.36 3 5 5 5 10 5 2 1 35 2.65.35 totals or means 2.4415 63 394 268 191 83 2732 1037 2.23.21 Table 28. Classification of Generation 13 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 2 1/4 3 30 12 17 4 167 2.22.032 and 3/8 4 40 50 46 24 5 1 172.35.022 1/2 4 32 34 47 26 8 2 1 154 2.40.10 2 and 5/8 2 11 21 41 28 3 2 108 2.47.15 2 and 3/4 15297 131 2.56.19 2 and 7/8 4786 126 2.43.44 33155 115 2.50.50 totals or means 2.5014 125 127 173 125 6 1 571 2.39.11 Table 29. Summary of the results of 13 generations of minus selection, based on tables 16 to 28. Generation. No of offspring. Mean, parents. Mean, offspring. Standard deviation, parents. Standard deviation, offspring. Correlation, parents-offspring. Absolute regression of offspring on parents. Advance of parents. Advance of offspring. 151.61.00.208.515.46 213 1.41.073.422.493.033.34.05.07 319 1.56 1.18.196.484.206.38.15.11 432 1.69 1.28.190.460.020.41.13.10 571.73 1.41.233.500.184.32.0 1.04.1361,25 1.731.111.283.091.285.049.4.285.079.1,058.1210 1.255.242.158.17.071.232.310.342.152.12.14.12 14.08 1357.2.39.177.317.235.11.06.16 total 11,704 Table 30. Mean grade and number of offspring produced by parents of a particular grade in each generation of the minus selection series, based on tables 16 to 28. The grade of the parents is indicated at the head of each column. In the body of the table is recorded the mean grade of the offspring, in light-faced figures, and the number of offspring, in heavy-faced figures. Generation. Grade of parents, below, grade and number of their offspring. Total number of offspring. 1 1/4, 1 3/8, 1 1/2, 1 5/8, 1 3/4, 1 7/8, 2 2 1/8, 2 1/4, 2 3/8, 2 1/2, 2 5/8, 2 3/4, 2 7/8, 3 1.34.85, 1.37, 1.058, 31 6 10 55 to 1.17, 1.45, 1.11, 0.67, 1.09, 1.10, 17 5 37 3 27 12 132 3 1.05, 1.04, 1.31, 1.22, 1.26, 1.96, 20 28 28 48 63 3 195 4 1.56, 1.16, 1.31, 1.36, 1.34, 1.18, 1.36 4 29 59 40 93 95 9 329 5 1.50 1.25 1.35 1.30 1.64 1.52 1.80 51 53 54 262 143 109 5 701 6 1.34 1.46 1.49 1.59 1.58 1.52 1.82 24 94 244 502 283 85 1252 7 1.55 1.67 1.65 1.72 1.74 1.93 1.62 1.88 2.28 1.875 32 330 969 260 41 4 15 18 6 1688 1.84 1.81 1.86 1.87 1.87 1.92 1.67 19 1173 77 36 3017 6 1726 9 1.90 1.93 1.93 1.91 2.07 811 403 148 175 53 1591 10 1.96 2.00 2.04 2.05 2.13 2.15 1.95 2.18 478 474 217 119 67 49 27 21451 11 2.08 2.15 2.13 2.16 2.21 2.20 2.26 1.95 51 183 318 268 81 5 226 5 984 12 1.98 2.14 2.15 2.11 2.24 2.32 2.45 2.51 2.65 10 118 166 230 242 137 42 5 335 1037 13 2.22 2.35 2.40 2.47 2.55 2.43 2.50 67 170 154 108 31 26 15 571 11704 Table 31. Results of a first return selection from Generation 6 series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/4 1/2 3/4 -1 -1 1/4 -1 1/2 -1 3/4 -2 3/8 2 1 3 4 8 8 26 1.08.65 eighths 2 2 3 4 10 14 17 24 76 1.33.71 3/4 1 1 2 1 5 1.30.65 7 eighths 2 2 1 4 2 11 1.41.63 Totals or means. 62 4 6 5 16 18 28 33 6 118 1.28.68 Table 32. Results of a second return selection from Generation 6 series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/2 3/4 minus 1 dash 1 1/4 dash 1 1/2 1/2 1 3 4 5 2 4 19.95.45 Table 33. Results of a third return selection from generation 6 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/4 1/2 3/4 minus 1 dash 1 1/4 dash 1 1/2 dash 1 3/4 minus 2 1/4 5 2 2 3 1 13.63.38 3/8 2 2 3 5 4 2 3 21.86.49 dash 1 1 2 3 4 3 13 1.61.49 9-1 1/4 1 2 4 9 8 5 2 31 1.35.10 Totals or means. 83 2 7 6 9 12 11 14 12 5 78 1.14.31 Table 34. Results of a fourth return selection from generation 6 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/4 1/2 3/4 minus 1 dash 1 1/4 dash 1 1/2 dash 1 3/4 minus 2 1/4 1 2 1 1 4 2 3 2 16 1.34 minus 1.09 1/2 1 1 1 2 5.70.25 eighths 1 1 1 3.83.21 3/4 1 1 1 2 1 6.83.087 eighths 1 2 2 2 2 1 10 1.17.30 minus 1 2 1 3 3 1 10 1.42.42 Totals or means. 63 3 2 6 4 7 10 8 6 4 51.17.54 Table 35. Results of a fifth return selection from generation 6 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. 0 1/4 1/2 3/4 dash 1 1/4 dash 1 1/2 1/4 2 2 4 1.00.75 3/4 1 3 4 1.12.37 7 eighths 2 2 1 5.25 plus. 62 Totals or means. 65 3 2 1 2 2 3 13.75.10 Table 36. Results of a sixth return selection from generation 6 minus series. Grade of parents. Grade of offspring. Totals. Means. Regression. Plus 1 1/4 plus 1 plus 3/4 and 1/2 and 1/4 0 1/4 1/2 3/4 minus 1 dash 1 1/4 dash 1 1/2 dash 1 3/4 1/8 1 1 3 2 1 2 2 12.29.17 1/4 2 1 1 4 1 4 13.35.10 3/8 1 2 1 1116.87.50 1/2 1121.5.25 plus. 25 Totals or means. 26 1 1 1 2 1 4 7 2 5 8 2 1 1 36.39.13 Table 37. Results of a return selection from generation 7 minus series. grade of parents, grade of offspring, totals, means, regression, a half 3/4 minus 1 dash 1 1/4 dash 1 1/2 dash 1 3/4 minus 2 3/4 1 3 3 7 8 3 25 and 7/8 2 2 2 2 8 totals or means. 78 2 3 5 3 7 10 3 33 1.15. 37 Table 38. Results of a return selection from Generation 8 minus series. Grade of parents, grade of offspring, totals, means, regression. 3/4 minus 1 dash 1 1/4 dash 1 1/2 dash 1 3/4 minus 2/2 1 3 6 3 13 1.69 minus 1.195 1 9 3 13 1.21. 59 7/8 222.00. 13 minus 1 1 2 4 4 2 13 1.56. 56 totals or means. 72 1 2 2 7 19 10 41 1.51. 79 Table 39. Results of a return selection from Generation 11 minus series. Grade of parents, grade of offspring, totals, means, regression. 1/4 dash 1 3/4 minus 2 dash 2 1/4 dash 2 1/2 dash 1 1 3 7 3 2 16 1.95. 33 Table 40. Results of a return selection from Generation 6 plus series. Grade of parents, grade of offspring, totals, means, regression. Plus 1/2 and 3/4 plus 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 2 1 1 3 3 2 2 3 1 1 17 2.36. 36 Table 41. Results of a return selection from Generation 11 plus series. Grade of parents, grade of offspring, totals, means, regression. 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 4 4 1/4 2 5/8 2 3 2 5 5 1 1 22 2 3/4 2 4 1 8 2 17 3 4 4 1 9 3 1/4 1 3 1 5 totals or means. 2.7923 10 6 12 10 5 1 53 3.32. 53 Table 42. Classification of the extracted hooded individuals obtained in the second generation from a cross between hooded and wild rats. Grade of hooded grandparents. Grade of extracted hooded grandchildren. Total. Mean. Mean, uncrossed race. Standard deviation. Standard deviation, uncrossed race. minus 2 dash 1 3/4 dash 1 1/2 dash 1 1/4 minus 1 3/4 1/2 1/4 0 plus 1/4 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 female sign dash 1 Gen 2.5, minus series 2 4 6 5 6 13 2 1 3 4 5 3 4 2 1 1 62 plus dot 31 minus 1.20 dot 98 dot 49 female sign minus 2, Gen 6. Minus series 1 1 1 1 2 6 6 7 2 3 6 4 2 4 1 1 48 plus dot 25 minus 1.59 dot 97 dot 44 female sign minus 2 and dash 2 1/4, Gen 10. Minus series 1 3 3 1 10 3 9 8 14 4 7 8 1 4 3 5 2 4 1 91 plus dot 24 minus 2.05 1.18 dot 24 female sign plus 3, Gen 3. Plus series 1 5 3 2 3 4 2 1 21 plus 2.56 plus 2.60 dot 50 dot 53 female sign plus 3 1/4, Gen 5 and plus 3 1/2, Gen 6. Plus series 1 2 1 1 1 6 9 8 8 1 38 plus 2.97 plus 3.14 dot 52 dot 49 female sign plus 4 1/4, Gen 10. Plus series 1 3 4 2 3 3 16 plus 3.15 plus 3.84 dot 28 dot 36 table 43 dot. Classification of the extracted hooded individuals obtained in the second generation from a cross between hooded and Irish rats. Grade of hooded grandparents. Grade of extracted hooded grandchildren. Total. Mean. Mean, same grade and generation, uncrossed race. Standard deviation. Standard deviation, uncrossed race. Minus 2 dash 1 3/4 dash 1 1/2 dash 1 1/4 minus 1 3/4 1/2 1/4 0 plus 1/4 and 1/2 and 3/4 plus 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 dash 1 1/2. Gen 3 1/2 1 5 3 6 12 26 9 9 10 1 3 2 2 1 90. Dot 62 minus 1.31 dot 61 dot 48 dash 1. Gen 4 6 3 4 5 9 14 8 1 1 1 1 53. Dot 73 minus 1.18 dot 60 dot 46 plus 2, Gen 7 1/2 6 6 12 11 8 3 4 4 6 1 3 1 1 66. Dot 94 minus 1.75 dot 84 dot 35 plus 2 1/4. Gen 2 3 4 5 4 16 7 16 22 25 29 24 13 33 14 8 8 6 3 239 plus 1.27 plus 1.80 dot 90 dot 75 plus 3. Gen 3211334221211123 plus .95 plus 2.50.87.53 Table 44. F generation produced by extracted hooded rats. F generation, derived from a cross of a hooded rat of the minus series with a wild rat. See Table 42. Grade of F. Parents. Grade of F. Offspring. Totals. Means. Regression. Minus 1/3 1/2 1/4 0 plus 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3/4 2 1 4 3 4 1 2 1 1 19 plus .04.71 2 1/2 1 1 1 3 2 2 1 5 3 6 4 3 1 1 34 plus 2.06.44 Table 45. F generation from minus series crossed with wild. Grade of F. Parents. Grade of F. Offspring. Totals. Means. Regression. 1/4 0 plus 1/4 and 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 2 1/4 2 1 1 3 6 6 9 16 25 14 10 2 1 96 1.78.47 2 3/8 2 1 1 1 6 3 8 3 9 4 4 1 1 44 1.67.72 7/8 1 2 1 1 1 1 18.91 1.96 3 1 1 3 3 5 9 5 7 3 1 1 39 2.02.98 3 1/8 1 1 3 1 2 5 4 1 18 2.82.30 Totals or means 2.523315 16 10 22 26 47 20 23 14 7 1 2 205 1.86.66 Table 46. F generation from minus series crossed with wild. Grade of F. Parents. Grade of F. Offspring. Totals. Means. Regression. 0 plus 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 2 1 1 3 3 2 12 15 10 2 3 1 53 2 1/8 1 1 1 4 1 4 1 13 2 1/4 1 3 4 1 2 2 13 2 3/8 1 2 3 2 4 2 14 2 5/8 1 1 2 1 2 7 2 7/8 2 1 1 1 5 3 1 1 1 7 4 14 Totals or means 2.272136 17 28 16 8 21 7 1 119 2.06.21 Table 47. F generation from minus series crossed with wild. Grade of F. Parents. Grade of F. Offspring. Totals. Means. Regression. plus 1/2 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 2 3/8 1 1 1 4 8 13 4 4 7 3 2 48 2.14.23 2 1/2 3 2 2 4 3 3 5 4 26 2.24.26 2 5/8 1 1 1 2 1 2 3 3 4 1 1 22.26.36 2 3/4 1 1 4 2 5 3 8 2 5 31 2.35.42 7/8 1 4 1 9 7 11 5 2 42.74.13 3 1/8 1 4 2 4 7 6 2 1 2 29 2.73.39 totals or means 2.692126 13 14 32 13 23 37 30 15 42 194 2.41.28 Table 48. F generation from minus series crossed with wild. Grade of F parents. Grade of F offspring. Totals. Means. Regression. 3/4 1 1 1/2 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 2 5/8 4 4 12 2 9 9 12 1 53 2.41.21 2 3/4 3 1 2 6 5 4 4 3 28 2.14.61 2 7/8 1 1 1 2 3 1 1 10 2.32.55 3 1 3 1 3 1 3 12 2.93.07 3 1/8 1 3 2 3 1 4 3 5 2 2 1 27 2.59.53 3 1/4 3 1 3 3 1 3 14 2.63.62 3 3/8 1 2 2 2 2 1 10 2.85.52 totals or means 2.803289 26 12 28 23 26 10 6 1 154 2.46.34 Table 49. F generation from minus series crossed with wild. Grade of F parents. Grade of F offspring. Totals. Means. Regression. 1 3/4 2 2 1/4 2 1/2 2 3/4 3 3 1/4 3 1/2 3 3/4 2 3/4 1 1 2 2.75 3 1 1 3 5 8 5 1 24 2.74.01 3 1/8 1 2 3 3 5 3 1 1 19 2.60.52 totals or means 3.082369 13 46 11 45 2.67.41 Table 50. Results of crossing the selected plus with the selected minus series. Grade of parents. Grade of offspring. Totals. Means. Standard deviation. -2-1 3/4 -1 1/2 -1 1/4 -1 3/4 1/2 0 +1 1/4 and 1/2 and 3/4 +1 +1 1/4 +1 1/2 +1 3/4 +2 +2 1/4 +2 1/2 +2 3/4 +3 1/2 Series 1. F generation, female sign -2, Gen 6, male sign +3 1/2 or 3 3/4, Gen 5 2 2 1 8 10 13 25 2 8 11 6 3 1 1 93 +.06.71 Series 1, F generation. -1 1 1 4 1 1 3 1 1 13. 57.66 1/2 1 2 1 3 3 2 1 1 1 1 16. 37.80 1 1 4 2 4 6 1 1 1 3 1 2 1 1 29 +.17.95 +1 2 1 3 3 1 5 1 4 3 2 3 1 30 +.03.97 +1 1/4 2 1 2 7 3 1 2 4 1 2 2 6 1 3 3 1 40 1 +.10 1.08 +1 1/2 1 1 1 4 2 4 1 1 1 1 1 18 +.06.91 +3/4 1 2 3 1 2 1 3 2 1 1 1 18 +.25.90 +1 1 7 3 6 13 4 8 5 5. 4 4 3 2 2 6 73 +.60.98 +1 1 1 1 2 1 3 2 1 1 13 +.61.83 +1 1 1/4 1 1 1 5 7 1 8 1 5 6 4 2 4 3 1 3 53 +.38 1.02 +1 1/2 1 1 0 Series 1, totals or means, F generation 1 4 9 7 22 24 26 20 49 10 24 24 23 10 20 13 7 5 7 305 +.24 1.01 Series 2, F generation. Female sign +3 3/4, Gen 10, male sign -3 1/4, Gen 10 1 1 1 2 4 2 1 1 1 14 +1.00.60 Series 2, F generation. +1 1/2 1 1 1 3 +1.31 +2 1 3 3 3 1 1 1 1 16 +.40.96 +1 2 2 1 1 1 7 +.82 +1 1 1 2 1 3 4 2 1 4 1 1 1 22 +1.03.97 +1 1/4 2 1 1 1 4 5 3 2 4 1 1 25 +.56.70 Series 2. Totals or means, F generation 2 4 3 8 8 12 9 6 5 3 5 2 2 1 2 1 73 +.72.87 Table 51. F offspring of the original mutant male, 4763, +5 1/2, mated with females of the plus series, and with the mutant female, 5153, +5 3/4. Grade of mother. Grade of offspring. Lower group. Upper group. plus 3 3¼ 3½, 3¾ 4 4¼ 4½ totals. Means. Standard deviation 5 5¼ 5½ 5¾ 6 totals. Means. Standard deviation plus 3 3/4 1 4 11 1 1 18 3.69 1 3 9 4 1 18 5.5 1 3 and 7/8 3 7 3 13 3.75 1 4 5 3 13 5.44 4 1 4 9 4 1 1 23.78 2 7 5 4 18 5.404 and 1/8 3 1 1 5 3.90 4 1 7 5.46 4½ 1 1 2 3.62 totals or means 1 1 12 31 9 3 1 58 3.73. 4 16 23 12 1 56 5.45. 23 mutant female sign 5153 plus 5 3/4 336 3.876 10 5.60. Table 52. F offspring of the original mutant male 4763 plus 5 1/2 mated with females of the minus series. Grade of mother. Grade of offspring, lower group. Grade of offspring, upper group. Minus 1 3/4 1/2 0 plus 1/4 and 1/2 and 3/4 plus 1 plus 1 1/4 plus 1 1/2 plus 1 3/4 plus 2 1/4 totals. Means. Standard deviation plus 4 1/4 plus 4 1/2 plus 4 3/4 plus 5 totals. Means. Standard deviation minus 2 1 1 1 3 1 2 1 1 1 1 13 plus dot 42 5 3 2 12 4.46 dash 2 1/4 1 1 1 2 2 2 3 1 1 14 plus dot 72 4 3 9 4.53 dash 2 1/2 2 1 1 4 plus dot 31 2 3 1 6 4.21 dash 2 3/4 1 1 2 4 plus dot 18 2 1 1 4 4.19 totals or means 2 1 1 2 7 3 5 4 2 3 2 2 1 35 plus dot 49 dot 77 6 11 6 6 2 31 4.43 dot 31 table 53 dot classification of the descendants through 3 generations of the 2 original mutants, male sign 4763, plus 5 1/2, and female sign 5153, plus 5 3/4. The parents are in every case of grade 5 1/2 or 5 3/4. Generation. Grade of offspring. Lower group. Upper group. 3 1/4 3 1/2 3 3/4 4 totals. Means. Standard deviation 5 5 1/4 5 1/2 5 3/4 totals. Means. Standard deviation F333.8764105.60 F1123.373151035.52 F17311.555 totals or means 1133.75.2524281751 Table 54. F descendants of the original mutant male, 4763, plus 5 1/2, mated with females of the plus series. Compare Table 51. Grade of F. Parents. Grade of F. Offspring. Lower group. Upper group. 3 3 1/4 3 1/2 3 3/4 4 4 1/4 4 1/2 totals. Means. Standard deviation 5 5 1/4 5 1/2 5 3/4 totals. Means. Standard deviation. Lower group parents 3 5/8 2 1 10 8 1 22 3.56 3 3/4 1 2 2 7 2 1 15 3.92 3 7/8 1 2 6 8 4 1 22 3.92 totals or means 2 3 14 16 16 6 2 59 3.78 33 Upper group parents 5 1/4 1 1 3.50 2 2 5.505 and 3/8 1 1 3 1 4 10 3.90 26 49 13 75.515 and 5/8 2 5 7 5.43 totals or means 1 2 3 1 4 11 3.86 35 2 8 56 13 79 5.50 15 Table 55. F descendants of the original mutant male 4763 plus 5 1/2 mated with females of the minus series. Compare Table 52. Grade of F parents. Grade of F offspring, lower group parents. Totals. Means. Standard deviation. minus 2-1 3/4 minus 1 3/4 1/2 1/4 0 plus 1/4 and 1/2 and 3/4 1 1 1/4 1 1/2 1 3/4 2 2 1/4 2 1/2 3 1/4 3/4 1 1 1 3.58 5/8 1 1 1 3 1 1 2 1 11.57 1/8 1 1 1 1 1 2 1 1 9.80 0 1 3 3 3 1 4 1 1 3 2 22.72 plus 1/4 1 1 1 3 1.00 plus 1/2 1 1 1 1 4.12 plus 1 1 1 1 1 1 1 2 1 9.19 totals or means 2 1 4 1 6 4 9 1 2 2 9 4 4 2 5 1 3 1 61.58 1.17 Grade of F parents. Grade of F offspring, upper group parents. Totals. Means. Standard deviation. minus 2 dash 1/3 minus 1/3 a half a quarter 0 plus 1/4 a half 3/4 1 1 1/4 1 1/2 1 3/4 2 3 1/2 4 4 1/4 4 1/2 4 3/4 5 5 1/4 5 1/2 L 1 U 2 L 1 U 2 L 1 U 2 4 1/8 1 2 1 1 1 1 1 3 5 4.85 4 1/4 1 1 6 1 1 1 1 10 4.62 4 3/8 1 1 2 1 1 2 4 4.56 4 1/2 1 2 2 1 1 2 4 10 6 8 4 6 6 41 4.78 4 5/8 1 1 1 1 1 2 3 2 8 4.91 totals or means 1 1 2 4 2 1 3 1 2 9 18 10 12 9 7 14 68 plus dot 75 4.77 1.03 dot 44 1 lower group offspring dash 1 3/4 to plus 2 inclusive 2 upper group offspring plus 3 1/2 to plus 5 1/2 inclusive. Explanation of plates. Plate 1. Top row, a set of arbitrary grades used in the classification of the rats studied. Middle and bottom rows, skins of rats graded as indicated by the numerals above each skin. The animals graded +4, +4 1/4 and +4 3/4, being entirely dark above, are shown in ventral view. Plate 1 Plate 2. Male sign 8000, a wild grey rat caught in Cambridge, Mass., October, 1908. Female sign 6176, a black-hooded rat of grade -1 3/4 which was mated with male sign 8000. Male sign 8021 and male sign 8018, F offspring of the pair just described, male sign 8000 and female sign 6176. Male sign 8021 is of grade +4 3/4, with considerable white below. Notice also his white legs and compare with those of his father. Male sign 8018 is of grade +5 1/2. Notice white areas on belly and front legs. 8075, 8078, 4F progeny, grandchildren, of male sign 8000 and female sign 6176. 8075 is black-hooded, grade 3/4, 8076 is grey, +4 1/4, 8077 is grey, +4, 8078 is black, +5 1/2. Plate 2 Plate 3. Male sign 103, an evenly marked rat of grade +3. A female rat of this same grade was mated with male sign 8000, the wild grey male. 2 litters of F grandchildren are shown in 8062, 8067, and 8070 to 8074. 8062 is black-hooded, +2, 8064 is grey-hooded, +2, 8065 is black, +5, 8066 is grey, +5 1/4, 8067 is grey, plus 4 1/2, notice white feet. 8070 is black-hooded, plus 2, 8071 is grey-hooded, plus 1 3/4, 8072 is grey, plus 5, 8073 is black, plus 5 1/2, 8074 is grey, plus 5 3/4. Plate 3. Asterisk 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 end of the Project Gutenberg ebook Piebald Rats and Selection asterisk 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 updated editions will replace the previous one, the old editions will be renamed. Creating the works from print editions not protected by U.S. copyright law means that no one owns a United States copyright in these works, so the Foundation, and you, can copy and distribute it in the United States without permission and without paying copyright royalties. Special rules, set forth in the General Terms of Use part of this license, apply to copying and distributing Project Gutenberg trademark symbol electronic works to protect the Project Gutenberg trademark symbol concept and trademark. Project Gutenberg is a registered trademark, and may not be used if you charge for an ebook, except by following the terms of the trademark license, including paying royalties for use of the Project Gutenberg trademark. If you do not charge anything for copies of this ebook, complying with the trademark license is very easy. You may use this ebook for nearly any purpose such as creation of derivative works, reports, performances and research. Project Gutenberg ebooks may be modified and printed and given away. You may do practically anything in the United States with ebooks not protected by U.S. copyright law. Redistribution is subject to the trademark license, especially commercial redistribution. Start. Full license. The full Project Gutenberg license. Please read this before you distribute or use this work to protect the Project Gutenberg trademark symbol mission of promoting the free distribution of electronic works, by using or distributing this work, or any other work associated in any way with the phrase Project Gutenberg. You agree to comply with all the terms of the full Project Gutenberg trademark symbol license available with this file or online at www.gutenberg.org/license. Section 1. General Terms of Use and Redistributing Project Gutenberg Trademark Symbol Electronic Works 1.0. By reading or using any part of this Project Gutenberg trademark symbol electronic work, you indicate that you have read, understand, agree to and accept all the terms of this license and intellectual property, trademark/copyright, agreement. If you do not agree to abide by all the terms of this agreement, you must cease using and return or destroy all copies of Project Gutenberg trademark symbol electronic works in your possession. If you paid a fee for obtaining a copy of or access to a Project Gutenberg trademark symbol electronic work and you do not agree to be bound by the terms of this agreement, you may obtain a refund from the person or entity to whom you paid the fee as set forth in paragraph 1.e.8. 1.b Project Gutenberg is a registered trademark. It may only be used on or associated in any way with an electronic work by people who agree to be bound by the terms of this agreement. There are a few things that you can do with most Project Gutenberg trademark symbol electronic works even without complying with the full terms of this agreement. See paragraph 1.c below. There are a lot of things you can do with Project Gutenberg trademark symbol electronic works if you follow the terms of this agreement and help preserve free future access to Project Gutenberg trademark symbol electronic works. See paragraph 1.e below. 1.c. The Project Gutenberg Literary Archive Foundation, the Foundation or PGLAF, owns a compilation copyright in the collection of Project Gutenberg trademark symbol electronic works. Nearly all the individual works in the collection are in the public domain in the United States. If an individual work is unprotected by copyright law in the United States and you are located in the United States, we do not claim a right to prevent you from copying, distributing, performing, displaying or creating derivative works based on the work as long as all references to Project Gutenberg are removed. Of course, we hope that you will support the Project Gutenberg trademark symbol mission of promoting free access to electronic works by freely sharing Project Gutenberg trademark symbol works in compliance with the terms of this agreement for keeping the Project Gutenberg trademark symbol name associated with the work. You can easily comply with the terms of this agreement by keeping this work in the same format with its attached full Project Gutenberg trademark symbol license when you share it without charge with others. 1.d. The copyright laws of the place where you are located also govern what you can do with this work. Copyright laws in most countries are in a constant state of change. If you are outside the United States, check the laws of your country in addition to the terms of this agreement before downloading, copying, displaying, performing, distributing or creating derivative works based on this work or any other Project Gutenberg trademark symbol work. The Foundation makes no representations concerning the copyright status of any work in any country other than the United States. 1.e. Unless you have removed all references to Project Gutenberg, 1.e.1. The following sentence, with active links to, or other immediate access to, the full Project Gutenberg trademark symbol license must appear prominently whenever any copy of a Project Gutenberg trademark symbol work, any work on which the phrase Project Gutenberg appears, or with which the phrase Project Gutenberg is associated, is accessed, displayed, performed, viewed, copied or distributed. This ebook is for the use of anyone anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. You may copy it, give it away or reuse it under the terms of the Project Gutenberg license included with this ebook or online at www.gutenberg.org. If you are not located in the United States, you will have to check the laws of the country where you are located before using this ebook. 1.e.2. If an individual Project Gutenberg trademark symbol electronic work is derived from texts not protected by U.S. copyright law, does not contain a notice indicating that it is posted with permission of the copyright holder, the work can be copied and distributed to anyone in the United States without paying any fees or charges. If you are redistributing or providing access to a work with the phrase Project Gutenberg associated with or appearing on the work, you must comply either with the requirements of paragraphs 1.e.1 through 1.e.7 or obtain permission for the use of the work and the Project Gutenberg trademark symbol trademark as set forth in paragraphs 1.e.8 or 1.e.9. 1.e.3. If an individual Project Gutenberg trademark symbol electronic work is posted with the permission of the copyright holder, your use and distribution must comply with both paragraphs 1.e.1 through 1.e.7 and any additional terms imposed by the copyright holder. Additional terms will be linked to the Project Gutenberg trademark symbol license for all works posted with the permission of the copyright holder found at the beginning of this work. 1.e.4. Do not unlink or detach or remove the full Project Gutenberg trademark symbol license terms from this work, or any files containing a part of this work or any other work associated with Project Gutenberg trademark symbol. 1.e.5. Do not copy, display, perform, distribute or redistribute this electronic work, or any part of this electronic work, without prominently displaying the sentence set forth in paragraph 1.e.1 with active links or immediate access to the full terms of the Project Gutenberg trademark symbol license. 1.e.6. You may convert to and distribute this work in any binary, compressed, marked up, non-proprietary or proprietary form, including any word processing or hypertext form. However, if you provide access to or distribute copies of a Project Gutenberg trademark symbol work in a format other than plain vanilla ASCII or other format used in the official version posted on the official Project Gutenberg trademark symbol website, www.gutenberg.org, you must, at no additional cost, fee or expense to the user, provide a copy, a means of exporting a copy, or a means of obtaining a copy upon request, of the work in its original plain vanilla ASCII or other form. Any alternate format must include the full Project Gutenberg trademark symbol license as specified in paragraph 1.e.1. 1.e.7. Do not charge a fee for access to, viewing, displaying, performing, copying or distributing any Project Gutenberg trademark symbol works unless you comply with paragraph 1.e.8 or 1.e.9. 1.e.8. You may charge a reasonable fee for copies of or providing access to or distributing Project Gutenberg trademark symbol electronic works provided that you pay a royalty fee of 20% of the gross profits you derive from the use of Project Gutenberg trademark symbol works calculated using the method you already use to calculate your applicable taxes. The fee is owed to the owner of the Project Gutenberg trademark symbol trademark, but he has agreed to donate royalties under this paragraph to the Project Gutenberg Literary Archive Foundation. Royalty payments must be paid within 60 days following each date on which you prepare, or are legally required to prepare, your periodic tax returns. Royalty payments should be clearly marked as such and sent to the Project Gutenberg Literary Archive Foundation at the address specified in Section 4. Information about donations to the Project Gutenberg Literary Archive Foundation. You provide a full refund of any money paid by a user who notifies you in writing, or by email, within 30 days of receipt that he does not agree to the terms of the full Project Gutenberg trademark symbol license. You must require such a user to return or destroy all copies of the works possessed in a physical medium and discontinue all use of and all access to other copies of Project Gutenberg trademark symbol works. You provide, in accordance with paragraph 1.f.3, a full refund of any money paid for a work or a replacement copy, if a defect in the electronic work is discovered and reported to you within 90 days of receipt of the work. You comply with all other terms of this agreement for free distribution of Project Gutenberg trademark symbol works. 1.e.9. If you wish to charge a fee or distribute a Project Gutenberg trademark symbol electronic work or group of works on different terms than are set forth in this agreement, you must obtain permission in writing from the Project Gutenberg Literary Archive Foundation, the manager of the Project Gutenberg trademark symbol trademark. Contact the Foundation as set forth in Section 3 below. 1.f1.f.1. Project Gutenberg volunteers and employees expend considerable effort to identify, do copyright research on, transcribe and proofread works not protected by U.S. copyright law in creating the Project Gutenberg trademark symbol collection. Despite these efforts, Project Gutenberg trademark symbol electronic works, and the medium on which they may be stored, may contain defects such as, but not limited to, incomplete, inaccurate or corrupt data, transcription errors, a copyright or other intellectual property infringement, a defective or damaged disk or other medium, a computer virus, or computer codes that damage or cannot be read by your equipment. 1.f.2. Limited warranty, disclaimer of damages, except for the right of replacement or refund described in paragraph 1.f.3, the Project Gutenberg Literary Archive Foundation, the owner of the Project Gutenberg trademark symbol trademark, and any other party distributing a Project Gutenberg trademark symbol electronic work under this agreement, disclaim all liability to you for damages, costs and expenses, including legal fees. You agree that you have no remedies for negligence, strict liability, breach of warranty or breach of contract except those provided in paragraph 1.f.3. You agree that the Foundation, the trademark owner, and any distributor under this agreement will not be liable to you for actual, direct, indirect, consequential, punitive or incidental damages even if you give notice of the possibility of such damage. 1.f.3. Limited right of replacement or refund. If you discover a defect in this electronic work within 90 days of receiving it, you can receive a refund of the money, if any, you paid for it by sending a written explanation to the person you received the work from. If you received the work on a physical medium, you must return the medium with your written explanation. The person or entity that provided you with the defective work may elect to provide a replacement copy in lieu of a refund. If you received the work electronically, the person or entity providing it to you may choose to give you a second opportunity to receive the work electronically in lieu of a refund. If the second copy is also defective, you may demand a refund in writing without further opportunities to fix the problem. 1.f.4 Except for the limited right of replacement or refund set forth in paragraph 1.f.3, this work is provided to you as is, with no other warranties of any kind, express or implied, including but not limited to warranties of merchantability or fitness for any purpose. 1.f.5 Some states do not allow disclaimers of certain implied warranties or the exclusion or limitation of certain types of damages. If any disclaimer or limitation set forth in this agreement violates the law of the state applicable to this agreement, the agreement shall be interpreted to make the maximum disclaimer or limitation permitted by the applicable state law. The invalidity or unenforceability of any provision of this agreement shall not void the remaining provisions. 1.f.6 Indemnity. You agree to indemnify and hold the foundation, the trademark owner, any agent or employee of the foundation, anyone providing copies of Project Gutenberg trademark symbol electronic works in accordance with this agreement, and any volunteers associated with the production, promotion and distribution of Project Gutenberg trademark symbol electronic works, harmless from all liability, costs and expenses, including legal fees, that arise directly or indirectly from any of the following which you do or cause to occur. A. Distribution of this or any Project Gutenberg trademark symbol work. B. Alteration, modification, or additions or deletions to any Project Gutenberg trademark symbol work, and C. Any defect you cause. Section 2. Information about the mission of Project Gutenberg trademark symbol. Project Gutenberg trademark symbol is synonymous with the free distribution of electronic works in formats readable by the widest variety of computers, including obsolete, old, middle-aged and new computers. It exists because of the efforts of hundreds of volunteers and donations from people in all walks of life. Volunteers and financial support to provide volunteers with the assistance they need are critical to reaching Project Gutenberg trademark symbol's goals and ensuring that the Project Gutenberg trademark symbol collection will remain freely available for generations to come. In 2001, the Project Gutenberg Literary Archive Foundation was created to provide a secure and permanent future for Project Gutenberg trademark symbol and future generations. To learn more about the Project Gutenberg Literary Archive Foundation and how your efforts and donations can help, see sections 3 and 4 and the Foundation information page at www.gutenberg.org. Section 3. Information about the Project Gutenberg Literary Archive Foundation. The Project Gutenberg Literary Archive Foundation is a non-profit 501(c)(3) educational corporation organized under the laws of the state of Mississippi and granted tax-exempt status by the Internal Revenue Service. The Foundation's EIN or Federal Tax Identification Number is 64-6221541. Contributions to the Project Gutenberg Literary Archive Foundation are tax-deductible to the full extent permitted by U.S. federal laws and your state's laws. The Foundation's business office is located at 809 North 1500 West, Salt Lake City, UT 84116, 801-596-1887. Email contact links and up-to-date contact information can be found at the Foundation's website and official page at www.gutenberg.org/contact section 4. Information about donations to the Project Gutenberg Literary Archive Foundation. Project Gutenberg trademark symbol depends upon and cannot survive without widespread public support and donations to carry out its mission of increasing the number of public domain and licensed works that can be freely distributed in machine-readable form accessible by the widest array of equipment including outdated equipment. Many small donations, $1 to $5,000, are particularly important to maintaining tax-exempt status with the IRS. The Foundation is committed to complying with the laws regulating charities and charitable donations in all 50 states of the United States. Compliance requirements are not uniform and it takes a considerable effort, much paperwork and many fees to meet and keep up with these requirements. We do not solicit donations in locations where we have not received written confirmation of compliance. To send donations or determine the status of compliance for any particular state, visit www.gutenberg.org/donate. While we cannot and do not solicit contributions from states where we have not met the solicitation requirements, we know of no prohibition against accepting unsolicited donations from donors in such states who approach us with offers to donate. International donations are gratefully accepted, but we cannot make any statements concerning tax treatment of donations received from outside the United States. U.S. laws alone swamp our small staff. Please check the Project Gutenberg web pages for current donation methods and addresses. Donations are accepted in a number of other ways including checks, online payments and credit card donations. To donate, please visit www.gutenberg.org/donate. Section 5. General information about Project Gutenberg trademark symbol electronic works. Professor Michael S. Hart was the originator of the Project Gutenberg trademark symbol concept of a library of electronic works that could be freely shared with anyone. For 40 years, he produced and distributed Project Gutenberg trademark symbol ebooks with only a loose network of volunteer support. Project Gutenberg trademark symbol ebooks are often created from several printed editions, all of which are confirmed as not protected by copyright in the U.S. unless a copyright notice is included. Thus, we do not necessarily keep ebooks in compliance with any particular paper edition. Most people start at our website, which has the main PG search facility, www.gutenberg.org. This website includes information about Project Gutenberg trademark symbol, including how to make donations to the Project Gutenberg Literary Archive Foundation, how to help produce our new ebooks, and how to subscribe to our email newsletter to hear about new ebooks.